Coors Field. Please take your seats and get ready for the presentations. Welcome all, welcome all. It's a beautiful day, a little bit chillier, but we're inside. We are not in the stadium, believe it or not. All right, everyone, thank you very much for coming to CryptoEcon Day here. My name is Mike McCoy. I'm the ecosystem lead here within the CryptoEcon Lab. CryptoEcon Lab, we do token economics as a service, a lot in the Filecoin Protocol Labs community, but also in the whole broader crypto world. Today I'm going to kick us off. I will be our MC Coy, whatever you want to call me, for the rest of the day, and we're ready to get this started. So I will begin. Now, within the field of crypto economics, CryptoEcon has very specific properties and is generally a financial tool and a financial research area that is strictly global. Today, most financial institutions, most financing for end users, for people in the everyday fiat world, mostly are prohibited by regions, borders, seas, mountains, etc. CryptoEcon, though, with the internet connection, allows us all to be able to connect through an economic level with cryptocurrency, with an internet connection, all throughout the world. And so we at the CryptoEcon Lab like to host these CryptoEcon Days to really bring together researchers, scientists, implementers, investors, and people in the space so that they could be able to learn and understand this very nascent field. Thanks to the combinations of cryptography and distributed systems, we have a lot more research areas and answers to try and find, probably more open questions than we have answers at the moment. And so bringing together some of the smartest people we know in this space to help other people understand what it is that we do in this space is very critical. For one, the general sentiment in crypto today, especially during a bear market, is that blockchains are good and tokens are bad. And a lot of it is too focused on speculations and scams, especially if some of the entities in crypto this past year that may have gone down or may not have made up their promises to certain customers. But to us in the CryptoEcon Lab, we believe tokens kick off and maintain growth in projects with global networks and partners. That you can be able to finance and be able to interact with people in many different ways through these different incentive mechanism designs that are so new into the field of cryptography, distributed systems, economics, etc. Now, one, I personally believe that tokens actually help within this cold start problem. The cold start problem is where you need to generate network effects, you need to generate users early on in a process of generating value. But in Web 2 today, so much of the cold start problem happens when venture capitalists are able to give and spend billions of dollars onto startups and to projects in the space. And a lot of times, that can be a lot of times it's a bet, more so than a guarantee or more so than a positive assumption. And you see in digital marketplaces, communication platforms, peer-to-peer payments, and social networks, that these are the examples of the ones that have actually become successful when lots of money has been pumped up early to them. But in Web3 specifically, we have the ability to finance from a bottom-up approach with end users that are able to put money and put their resources, put their time into projects that they believe are valuable, that they believe are worthwhile. And tokens are able to bootstrap this cold start problem to help mitigate that problem and to create generally native communities that could no longer or could not be able to connect together prior to this new phenomena. Think about it. Think about the people in the room today, right? I'm based in Philadelphia, Pennsylvania. I'm meeting people that are from all over the world today talking about a nascent topic that I probably wouldn't meet half of you if it wasn't for this type of environment. And that is a really cool community and a really cool problem we're trying to solve. So here's some key use cases on where and how you could utilize tokens when you want to grow users, when you want to build loyalty, you want to capture value, utilizing product, or generating rewards or dispersing revenue. For one, I believe starting up crypto native people starting up these networks natively with people that have specific interests to find your first 100 fans, to find your first 1,000 fans is something that crypto is a really good value add to. And we also believe in royalty programs are things that tokens really incentivize and truly bring more value to. But then in fields like MEV that we're going to talk about today a whole lot with our presenters, capturing value in more creative ways. MEV has been extracted in value in Web 2 and fiat worlds for at least the past 100, 120 years, but there are more creative ways you could be able to extract value as an end user rather than just being a large entity as well. And of course, we know about DEXs and DeFi protocols and market makers and AMMs, and we're going to discuss a lot of those new type of tools and type of technologies that can be able to disperse revenue and disperse value a little bit more simply and a little bit more creatively today as well. But to me, in particular, crypto economics are meant to create global collective action, and that is why you are all here today. And that's why we are all here, to learn about the space and be interacting with this new type of technology together. So one, I wanted to highlight what we do at the CryptoEcon Lab before we get into CryptoEcon Day. We at the CryptoEcon Lab do crypto economics as a service. So we can help with token design, mechanism design, simulations and modeling, economic audits, and then also help with protocol improvement proposals and protocol governance. We've done this for at least the past 3 years with ZX, who's our team lead, and others that have joined our team in helping with improvement proposals and helping with building the Filecoin economy, as well as helping other Protocol Labs network startups within that economy, or within that network, build out their incentive systems. But now we are looking to help out not just within the Filecoin Protocol Labs community, but outside in many different ecosystems and protocols and foundations and venture portfolios. So if you and your team need assistance in this field, we'd love to help you out, love to build out incentives with you and others to give long-term success and not just short-term pump and dumps. And what you can expect today, here are some topics that we will be able to cover at CryptoEcon Day. The economic impact of the Filecoin virtual machine, which creates this new financialization on top of data storage models, multi-dimensional fee markets and gas economies as well, quadratic funding with Gitcoin, replicating market makers with Numia, I always get that word wrong. And we'll have Vic talk about island economies and how Bitcoin, Ethereum, and Filecoin have their own individual island economies, as well as some new trends in Ethereum and maximal extractable value. And Tarun Chitra will discuss NFT auction designs and some of those new capabilities they present. So we are honored to have you all here with us today. We're honored to get the show going. And one, we want to highlight that we are also going to be in Austin on April 25th of this year for CryptoEcon Day Austin. And there we're going to have David Shuttleworth from Binance Labs, Miko from Gumi Cryptos, David from Lit Protocol, and Giosun from George Mason, and a whole bunch of researchers from our team and 6-Man Ventures that will be able to highlight more new, incredible, exciting topics within crypto economics come April 25th of this year. And with that, I believe, and if you want to be able to sponsor future CryptoEcon Days, one, we want to thank our sponsors today in Solaris and in Protocol Labs for being able to sponsor us and be able to bring all of you into Coors Field today to learn about this field. But if there are any other events, whether we are going to be in Austin, whether we're going to be in Paris or Singapore this year, that you would like to support this community, that you would like to support the team at CryptoEcon Lab in bringing more knowledge into this space, please let us know. You can email us, you can talk to me during the event or after, and we can get you involved into that. So without further ado, welcome to CryptoEconDay Day Denver. And next up, thanks if you want to clap. Yeah. And next up, we have two very special people who will be getting into the details of the FVM and talking about the economic implications, economic implications of the Filecoin virtual machine. We have Jonathan Victor and Sarah Thiam. Right on. Hello.
Hey, I guess we just stand here. Hey, nice to meet all of you. My name is Sarah. Good to meet you. I'm from the Filecoin virtual machine team, which I'm sure many of you have heard of. I'm a developer advocate looking after developer experiences. Really happy to meet all of you today.
Can't tell if that scratchy noise is me. Hopefully not. Great to meet everyone. My name is Jonathan Victor. I'm one of the ecosystem leads at Protocol Labs. I've worked on a number of things from like the research side of Filecoin to the product side. I lead a lot of our BD work at the current moment. So yeah, super excited to talk about the economic impact of the virtual machine.
Yeah, so just to get a show of hands, how many of you know about, oh, hello? Oh, this is so much louder. Hi. Hi, nice to meet all of you again. Just really quickly, I'm from the FVM team doing developer experience. My name is Sarah, and this will be JV, and we'll be covering a fireside chat around what we think on the economic impact of Filecoin virtual machine on the Filecoin network. So for how many of you here know what the Filecoin virtual machine does? Awesome, awesome. Okay, so I see some hands here. Don't worry if you're new to it. I'm going to give you a really high-level intro to it. The Filecoin virtual machine enables programmability around storage, which is very different. So let's say you are a smart contract dev today. A lot of your smart contracts itself will have to write to storage separately outside of the platform that you're using. That also leads to higher costs. What we aim to achieve with the Filecoin virtual machine is that you can do that all within a native environment. Right now, we have Ethereum compatibility, which is why we're here at ETH Denver this whole week. You are able to use your familiar EVM tooling to then deploy a smart contract into the Filecoin network and access the storage that is stored there. So that should enable a lot of dApps being created. We see a lot of potential with web scale applications there. So yeah, I hope that gave you a good overview to those of you who are new to the FVM. And I think let's get on with what we think about the economic impact. How do I press the next slide? Cool. So this is kind of the structure that we're thinking of today. These are some points that JV and I were kind of going back and forth on, and I'm sure some of you have these questions in mind as well. Do you want to kind of take us through the structure of it?
Sure. Yeah, I mean, so I think one of the things that's interesting to first maybe talk about is Filecoin as its own economy. Vic is going to talk a little bit later about this metaphor of island economies. But I think specifically when we think about the FVM, it's really unlocking sort of the composability inside of Filecoin's own version of that. In order to sort of like underlie and like motivate some of what the economic potential is that's unlocked, it's also probably useful to understand what the FVM actually means in terms of like what are the functionalities, what are the services that now are possible inside of the Filecoin economy. And then maybe we can talk a little bit more about what are sort of the roadblocks, what are the things that have to be built out in order to enable new use cases and things on that front as well. And then we can talk about the risks and some of the things that, as we collectively as a community go together, we'll have to sort of tackle along the way. Yeah,
we're not going to be shy about the risk, but these are open questions, and we're always around to take more questions, and we hope to have some time for some Q&A later on. So yeah, let's start with the economic potential of Filecoin with FVM. As I mentioned earlier on, from my view, so one of the things that I do in the FVM side of things is to lead an early builders cohort. That's a cohort that has been building for about 6 months now. Yeah, we opened it up in October last year when we were just starting out on the Ethereum compatible version of the FVM. And we had up to now, we have about 170 teams and projects that have signed up to build with us till then. So we see a lot of interest, and we've seen a lot of use cases. Potential of Filecoin with...
Oh.
Hello? Yeah. So as I was saying, we've seen a lot of use cases being built out, and a lot of them have the potential to replace or be a good complement to the Web 2 solutions that we see today. And so we see a lot of opportunity for scale across the industry and being able to bring the Web 3 industry as a whole into the mainstream.
Yeah, I mean, sort of taking one step back, one of the things that kind of sets Filecoin apart from other ecosystems is Filecoin itself is trying to build a bunch of real-world services for crypto in general, but also just for society. So right now we have one big service. We have a giant storage network, which is all anchoring into the same block space. But eventually we'll have retrieval markets, we'll have compute over data. It's largely just talking about what are these different services that you can now trigger from smart contracts from Web3 to go do off-chain things in the real world. The thing that the FVM allows us to do is to now start writing services around that. So if you had the ability to write a data service before where you could contract a storage provider to go store some data in the real world, you can now compose that with other features of Filecoin state to say, well, how do I make sure that there's always 10 copies of my data on the network? If one of them falls off the network, how do I automatically allow someone to get a bounty for restoring another copy? The FVM gives us the expressivity to start writing these programs that can now sort of trigger other services to happen outside in the real world. When we start thinking then about storage, retrieval, compute, sort of all of these different things that you want to do with data, the FVM is allowing us to create the composability between these building blocks, not only around the services, but then also the remuneration for those services. So when you think about what is the role of DeFi, today, DeFi, this is, I guess Mike sort of talked about it, but like it's a little bit of turtles all the way down. It's like people flipping tokens back and forth to each other. I think the cool thing for Filecoin is when we start thinking about the services that are being rendered, you may want to be able to, like, as a storage provider, borrow against the cash flows of people who are like paying you to store their data in order to finance your growth today. So I think this is like, when we think about what does the FEM unlock, it's really thinking about both the data services and how do you create more composable and more powerful offerings for the world. But then it's also on the financial side with what are the different ways in which you can now transfer value and create more bespoke products around that.
Yeah, so one thing that I'm kind of curious, I thought it was a really good discussion that we had around was like, if we think long term, right? So not even right, so right now, very nascent, a lot of these teams are we just released like this new version and we're actually launching on March 14th. And that will be the first version of the FEM. And then later on in 2023, we'll see a native version of the FEM, which will enable many more languages to build on the FEM itself, which will then allow all these developers that are used to different languages to build different solutions, they will then be able to come into FEM. If we think a little bit longer term, let's say like 30 years, 20 years or so, what do you think is the potential of that as a whole industry?
So I think like one thing that's kind of interesting to think about is like the split between like the digital and the physical worlds. So like think about a game as an example, right? Like you have a game economy, like you can actually build an economic system. There's tons of people who are thinking about like how do you build these games that are self-sustaining economies, things like that. Once you have a connection where you can actually pay for infrastructure in those tokens, you could actually have a game economy where from the actual game economics and mechanics, you can fund the distribution, the storage, the actual running and operation of the game. It's not like you need someone individually to then like go drop a credit card with AWS or whatever else. Like literally the digital world can fund itself. And so I think this is like one area where when we really think about how do you like take the crypto economic rails that Web3 in general has and start bridging it to more and more services, this is like one area where Filecoin's sort of enabling the bridging between like what are the real world services we need to like move data around and to process data, to do all the things that people expect, and everything that blockchains are currently enabling us to do to think about like transfer of value and build these more sophisticated systems.
Yeah, so maybe I can share a little bit about some of the key use cases that we see. We have some big bets as well on what we think can be built with FEM. I mean, of course, there are many industry solutions at large which go into different specific problem statements, but in general, we think that there are a few areas that are big bets for us with the FEM. One of them being perpetual storage. So if none of you have heard of that term before, it is what it sounds like. It is about storing your data and allowing it to be perpetually stored. Of course, with a certain fee that comes with it, but then you don't have to worry about your data disappearing at some point or not having enough replicas of it. We have a few solutions building that out right now, and we see a lot of dApp developers actually taking those solutions as SDKs or simple CLIs and putting into their solutions, and that has really enabled a lot more scale with the kind of solutions that we see. Right? I think about like 30, 50 have come up ever since those kind of primitives or building blocks have been built. The other big thing that we see as a big bet for us is around decentralized compute. We have our Bacalhau team in the room today. If you have not heard of that, that is our compute over data framework. We think decentralized computation would be really interesting to see. Right now with FEM, to be clear, it allows programmability around storage, but you are programming the metadata of the storage deal on the Filecoin network. So you are able to manipulate the behavior of where your data file goes and how it's being used within your application, but you're not able to access the data inside. Whereas complementing FEM and using it to orchestrate jobs on decentralized compute will then enable what we see a lot in Web2 today, which is around analytics, around computation, and so on, right? So we think that that's a huge big bet for us as well. A few interesting use cases that I've seen built out are like decentralized AI model training, decentralized AI model traceability, where you can mint an NFT for every data that's added to the model itself, and then you can trace how that model is being built and check out what the bias of that is, right? So I think there are a lot of good, and I can go on, but there are a lot of good ideas in that space as well, so that's also really key to us. The third one is around access control. In blockchain today, and I think the big difference with Web2 is that it's great that it's transparent, but at the same time, privacy is an issue. And so with access control of FEM, which is enabled through things like at the threshold cryptography or enabling encrypting and decrypting off-chain and then bringing it on-chain with FEM, we see that that allows more real-world solutions to be built out. So for example, we've had NFTs be created, a new NFT standard where you can actually have a hidden file and then have a preview of that file at a more low-res image or maybe something else that you want to show within the NFT, and then that can be sold and shared around with different people in the marketplace. So I think there's just a lot of opportunities here which then can lead to the composability that JV was talking about earlier on.
Yeah, and maybe just to build off of that, I think when we think about things like access control, it really is actually like necessary pre-steps to, if we think of like data DAOs in the sense of like people can contribute data into some sort of like organization, you can then like monetize that and say like, if some external org wants access, they have to pay for it. I think like that sometimes sounds kind of theoretical, but you could almost squint at what's going on as people talk about AI, ML, and like where is the value capture going to end up happening. Like one of the interesting features is like statistically, like as we keep adding more like all the LLMs, like eventually there will be convergence to like what are the model weights that people are looking at. And the things that will go into that, or the people who will have the moat is like who has access to bespoke data sets to actually feed into these models. So like whether you're talking about Web 2 or Web 3, this idea of like how do you do permissioning for data and what gets included in these models, there are problems that have to be solved. Web 3 has to solve them much earlier because by default we are storing data on untrusted servers. We have to figure out access control from the get-go. But as a result, it means that we have the ability to do the permissioning and do the value transfer back that you might want to do if you say like, if OpenAI is going to train a new model, like if they want access to your data, how do you enable them to say like, we will give you like 0.00001% of whatever like future revenue they have in order to include you in the corpus of their data. So I do think like these primitives are really important. Sometimes it can feel like it's very far off, but I think as you sort of see the trends of where everything else is going, it feels like these things are converging. The thing that's exciting to me is like these are problems that have to be solved in Web 2 anyways, but like we are actually probably further in doing this because we don't have the luxury of just saying like, well, we'll just like trust that someone's going to hang on to the data, that they'll like permission it properly, that they'll like send value back properly. We just have to solve it first.
Yeah, I really like that point around, I think, value attribution. I think that's a huge part, right, which I think can be solved with what we are building over here with all the different solutions that are coming out. So yeah, the other thing, I think maybe segueing into the next point is around what is the impact of FVM on the Filecoin economy itself. So I think this more touches on like the fill, the price of fill. How will FVM change that, right? So one mental model that I have is around like demand and supply, just really simply demand and supply, right? So I think what the FVM will do is really to drive up demand of fill. That really comes with the network utility that we'll bring to the network itself once FVM is incorporated into Filecoin. So if you think about like we have storage, and storage has taken us a while to build out. Now we have a really strong foundation. Data onboarding is happening. Then next comes compute, and this is where FVM comes in, right? So now you are able to, I think for the first time ever, and we've seen this in a lot of hackathons, first time ever is very real for me and my team that has experienced this in hackathons, where developers are like, oh, we always thought, you know, we've only seen Filecoin for storing data. We've actually not interacted with the Filecoin protocol. We've not actually tried to build apps from that. And now people are starting, and we're building a lot more documentation for that. So compute will be the next part that comes in, and then FVM itself will also enable retrieval markets. And it does play a big part in the retrieval markets roadmap that is coming up. And so once you have storage, programmability, compute, and then retrievals, that will increase the network utility a lot more, and that will really drive up the demand of fill. I mean, of course, that comes with the other side, which is the supply of fill. Yeah.
Yeah, I mean, I guess like one thing that I think about with the FVM and what it enables, there's actually, like Filecoin is a base protocol. I think you could sort of look at it and see like storage providers need access to capital to like grow their businesses. So when they're like locking it for committed capacity, when they're doing it to like add data to the network, like this is actually like a service that they're probably going to like the outside world. Either they're buying Filecoin off of an exchange, or they're borrowing it from a lender, whether it's Anchorage or Dharma. And one of the things that's kind of interesting is like with the FVM, you can actually do this stuff inside of like the blockchain itself. And you can say, like this is actually where DeFi has a strategic advantage, where like in the same moment that someone is like striking a deal, they can borrow capital at that exact moment without having to pay interest in advance. They can pay it only when they're also earning revenue. And so like when we actually think about like what does the FVM unlock, it's like actually enabling like better capital efficiency because you're strapping like the capital markets directly on top of the services that are like being run underneath. And then as you sort of extend that analogy out, you can start seeing like other ways in which the FVM can enable better like markets on the network itself, whether that be in terms of like rehypothecating like the staked collateral and fill to secure other protocols that are built on the network, whether that be like data auctions or other like compute networks, things like that. Or being able to use it to be able to like enable storage providers to like finance their businesses better, to be able to like actually take the cash flows that they have, use that to grow today by selling off like their future revenue. I think we start seeing like more interesting use cases around like what people actually want to do with the network.
Yeah, I think on the storage provider side, so we have a lot of people that are really interested on that piece, and I think that also comes into how it affects the economy, right? So on storage provider side, a large thing that they always try to think about and overcome is how do we get more liquidity to enable more storage providers to join the network, right? So if you're starting out new, you might not have the funding that is enough to buy the hardware, and so on and so on. So with FEM, we see solutions like liquid staking and under collateralized lending, which allows more storage providers to then come onto the network. What this also means is that more fill and more collateral will get locked up in the network, and so from my point of view, I think that also reduces the supply, and then also that, with demand increasing and supply staying the same or being reduced, it also drives up the price of fill. So really optimistic on that front. Of course, this comes with certain limitations and certain risk, which we'll cover in a bit, but that's how I kind of see a large part of it coming in play with the FEM.
Yeah, I mean, I think like one of the things that also sort of comes up, I don't know if people have heard of IPC or interplanetary consensus, like as more and more use cases, like I think like one of the interesting features of like how the Filecoin economy is sort of built is we have like this native economic loop of like people who pay for data. Like people are storing data, they will retrieve data, they will compute over data. And so like eventually as you have both like the data services that people are like triggering and running through the FEM, as well as having some of these like capital services to help enable better capital efficiency or allowing for just like the programmability of like value transfer, eventually, like we'll see like the Filecoin base layer have like pretty heavy demand for like its block space. I think that's where things like IPC, just being able to like offload that, so scaling solutions that allow us to basically take what are the parts of state that don't need to run at like the L1 layer with like all of the nation state security, global censorship resistant stuff that's not necessary for every use case if you're building a chat app that's like not really what you need. And so instead being able to move that into like subnets where you can operate with higher throughput, maybe less guarantees, but you can keep the value at different parts of like these layers. So I think like, honestly, we're like still quite early. There's so much stuff that has to be built.
There's so much. I mean, it hits mainnet, and then we also have to see like what kind of gas consumption that will run, that will take up on the network, and then we'll have to see like what is the appetite for the network to, the different network participants, the developers, and then the SPs themselves to then function in the network. I think the CryptoEcon Lab is looking very much into this, and at the end of the day, like we have many ways of thinking about it, and we are planning ahead, but we also have to see what really happens once applications with FEM start to hit the mainnet itself. Yeah, so on this point, like I think we have a lot of questions in our mind around like limitations or risk that we foresee. We don't really have the answer to it, but I think it's kind of good to like run through some of the thoughts that we have.
Sure.
Yeah. So one of the things I think you brought up was around the IPC coming into play. Chain bandwidth is something that we're definitely thinking about. How much will the FEM take up? How many apps will we actually attract? One of the things that we on the use case side have been thinking about is when, because there's so much collateral locked up in the Filecoin network, it does attract a lot of DeFi, right? DeFi in the sense that, DeFi for the right intent or DeFi for the wrong intent. So will applications come in where they're just trying to run DeFi applications that pull out collateral from the network, and is it being used for value generation? So I think that's something that we have to keep an eye out for, especially on the DeFi side. Yeah, I think that's one thing that I'm seeing in the builder ecosystem.
Yeah, I mean, I guess like a natural one that I'm sure people are thinking about too is like the moment you have like capital markets that form, MEV is going to show up as well. And so thinking through like how does that affect the blockchain as well. I know there's like a number of teams that are thinking about different solutions through like threshold encryption and like or time lock encryption and other like sort of approaches to sort of mitigate. But I think this is like broadly, I think a topic that hits every network at every point. And so I think it's something that we also are like trying to keep an eye out for like how that might affect things.
Yeah, and then on the point on like gas as well, I think gas estimation is something that we are very much trying to get a firmer grasp on. I think we have a pretty good gas estimation model in place right today, but we still need certain benchmarking to make sure that that doesn't increase too much. We also need more fine-grained control over how we use gas, which is something that we're implementing. So, for example, making sure that we are calculating it the right way, that when FEM hits the mainnet, maybe some system calls from previously that have been free previously are now going to be charged because of how often it's going to be used, or allowing people to have better control over the kind of syscalls that they want to call within their smart contract or their application itself. So I think gas is a big part, and because of this, like if the gas fees go too high, then it could really jam up the network and cause like bigger issues there. So that's something that we're very much like anticipating and wanting to see what happens when mainnet launches itself. Yeah, so I think these are just some of the risk and limitations that we are thinking about, which we don't really have the answer on. But yeah, I think we have to keep the conversation going and really keep an eye out and be super agile on how we want to respond to that.
Awesome.
Yeah, we have some time for Q&A, maybe. This is like a riff that, I mean, we are really early in the FVM stages, and these are really important questions that we have been riffing off of between our teams on the ecosystem side and also on the Filecoin engineering side, the FVM team itself. So super open conversation. Would like to take any questions from the crowd. Yeah, I see one question over there.
Check, check, 2.
Thanks so much. Love the conversation. And quick follow-up around the FEM blockchain. Is there any demand or need for bridges between other blockchains or other ecosystem components, or maybe it'd be more of a standalone blockchain on its own? I'd love to hear your thoughts about like the demand that you're hearing for bridging to other use cases.
Great question. Cross-chain bridging is in high demand. We do get a lot of app developers that are asking us to enable that. We have certain partners that are in discussion with us right now, and I think that will very much come out at launch on March 14th. We will have some partners that are on board with us, and then we'll keep building out as we go along. But definitely a lot of demand on that.
Yeah, I mean, I guess like 2 ways to think about it. There's folks who are interested in taking assets they have on other networks and then being able to use it inside of Filecoin's economy. So if you're a storage provider who is like dual mining on another network, you may want to be able to use like Ethereum as collateral to borrow Filecoin to then stake on the network without having to sell your Ethereum, things like that. But you also might have folks who are just looking at the cross-chain messaging side. So one of the unique features of Filecoin as an economy is like we have a very large storage network, soon retrieval and compute. And so being able to say, like, from Solana's ecosystem, if I can send a message into the Filecoin network to say, like, please persist this CID, someone please keep this copy around. Like, that's a net new functionality that like doesn't really exist for the Solana network, but they can now contract out to have that happen from the Filecoin side.
Yeah.
I think you mentioned there's 170 projects already building on the FBM. I was wondering if you had any comments around like the generalizations of what sort of projects they're building and what sort of demand you've seen.
Yeah, great question, because just did an analysis this morning, so I have some stats that like would not normally be in my mind. But I think out of the 176, and also bear in mind that these have been running for 6 months, we do see some projects like taper off, or they are taking a break and then they'll come back on later. So it's not a full 176 that will be active. Once we ship the mainnet, we expect about 100 to come in, and we're pretty optimistic on that. But on the split, we see a strong interest around infrastructure and tooling. So that's about 20% of the projects. Which is great, because we do need, I mean, something so new, we need a lot of tooling like block explorers, indexing, and so on. So we see a lot of people building out these tools for developers to use, and where we want to get to on that, and I think where it's headed is that a lot of these, for example, integrations with popular DApp tooling. So like push protocol is one really good example. We've had hackathons where developers themselves have started to build integrations with push protocol to get notifications in their dApps. So I think on this piece, where we want to get to is that we are able to provide like a really easy list and like models and examples for developers to take all these integrations and then build it out into their dApp really quickly, rather than trying to figure out how to build all these tooling out themselves, and then it takes them such a long time to get to the full solution. So we're super excited on that side. The other big piece that people are interested in, I think about 10% are data DAOs. So I don't think we covered too much on data DAOs this time, but that's a really unique piece that will come out from the FVM on Filecoin, right? You won't really get this with many other blockchains, purely because we are a storage network. So data DAOs themselves, if you've not heard of the term, is a DAO, as you know it. but then centered around key and valuable data sets as determined by the community. So we see a lot of people building out solutions there, using FVM to be able to upload a piece of storage via voting, and then have governance of that storage. However you want to build it, right? This is just an example workflow. Governance of that storage, allowing external parties to pay to access that storage, and then taking that profits and putting into the treasury of the DAO to then support the members of the DAO. So we see a lot of use cases there. So that's about 10%. Sorry, I'm going like really deep, but like, I'm just really excited with all the builders and the use cases coming up. Another 10% would be around DeFi. So like JV said, DeFi is a really big piece where enables cross-chain bridges. It's a large part of that, and also DeFi solutions to support storage providers on the network. So that's about 10%. And then the last one that I think would be key before it hits like 5% and below is around what was the last one? Around perpetual storage and storage solutions as a whole. So a lot of people are building platforms where you can very easily upload your storage. You don't have to deal with the storage deal making, which you can do, but it is a process and it is pretty technically heavy. So a lot of people are building easy platforms to use that, and then building different features upon that platforms that lead to different problem statements that you want to solve in different industries. So a good example is like we have Lighthouse Storage that has built perpetual storage that also allows for access control and encryption. We have the DeSci DAOs that, with the DAO also have like Lagrange DAO, right? It's a DeSci DAO, allows easy upload of your data sets, allows that whole governance piece I talk about in data DAOs itself, but it also allows for decentralized compute of the data sets within the DAO. So we see a lot of pieces being pulled together into solutions, and then it gets harder and harder to put it into certain categories, and we really encourage developers to take different pieces of the tooling or different pieces of what FVM can enable and put it into a whole solution for people out there who might not actually know about Filecoin and might not really care too much, but then they're like, oh, this is really a game changer and really going to solve a problem there in the world. So yeah, long answer to your short question, but that is kind of the split that we see. Yeah.
Any other questions?
Cool. If not, JV and I will kind of be around for a while, and if anyone has questions, we are here. Yeah, thank you so much. Oh, and if you want to find out more about FVM, there's a link tree over here, and it has like everything you need all in one. Yeah, thank you.
Everyone make sure you give a scan to the link tree over here to learn more about the Filecoin virtual machine. All right, so next up with us here at CryptoEconDay Denver, we actually have Theo Diamandis from MIT and Bain Capital Crypto, who will be discussing a mechanism for pricing non-fungible resources toward multi-dimensional fee markets. Now, Theo is currently a PhD researcher at MIT and also is on the research team of Bain Capital Crypto. You're going to hear a lot of interesting discussions here about multi-dimensional fee markets, first here with Theo, and then specifically on gas economies in Ethereum and the Filecoin economy with JP afterwards as well. But excellent to have Theo here with us. I first actually met Theo at a Columbia cryptoeconomic workshop that was in New York in December of this past year. He really took the room over and made everyone think a little bit deeper about how to structure fee markets. So without further ado, let's bring Theo on to tell us more.
Cool. Hello, everyone. So my name is Theo, and we're going to talk about multidimensional fee markets, which are one way that we can have our transactions be cheaper and get executed faster. Is this the... And I'm a PhD student at MIT, and I also do research with Bain Capital Crypto. Okay, so one thing that's kind of the premise for this talk is that fee markets with fixed relative prices are inefficient. So these are one-dimensional fee markets. And the framework I'm going to introduce today is how to optimally set multidimensional fees. So first, let's dive into this point a little bit of like why are transactions so expensive on almost any blockchain that exists today that has a lot of usage. So Right now, for the most part, all opcodes, for like the EVM, for instance, have fixed relative prices to each other. So an addition might cost, say, like 3 gas, and S storage costs like 700 or something like that. And so if the gas price goes up, both of these things get more expensive. And the potential mismatch between the demand and the usage can lead to things like denial of service attacks. So one kind of famous one was in 2016. The Ethereum network kind of got very, very slow for quite a bit of time because this X code size opcode was mispriced relative to its resource consumption. In this case, the resource being disk read. And this was updated in EIP 150, but had to be essentially manually adjusted. And we don't necessarily want to run manual gradient descent every time there is an attack like this. Of course, the other thing that fixed relative prices do are they limit throughput. So for instance, here's a very, very toy example, but let's say we have a mempool. We have a bunch of transactions. They either consume only CPU, so only compute, or they only consume bandwidth. And let's say the transaction submitters get a utility of 4 for the CPU ones, utility of 2 for the bandwidth ones, and the cost of each of them is the same. So if we consider a one-dimensional market where gas cost is 3, well, we're going to submit all the CPU ones because the net utility is going to be 1. However, we're not going to use any of the bandwidth resources of this block because the utility is too low. So we'd have negative utility if we were paying a gas cost of 3 for these. However, if we had a two-dimensional market, then we could have a different cost for using compute and using bandwidth, in which case we would have all the CPU transactions again, but also all the bandwidth transactions. And obviously, kind of from a throughput perspective, this situation is much better than the previous one. So this leads us to conclude that orthogonal resources, so things, for instance, if it's only compute and only bandwidth, these things should be priced separately. And of course, the natural question, and I'm going to say this is not something that we came up with. A lot of people have been talking about multidimensional fees for a very long time. But what we tried to do is come up with a mechanism of how to actually design these fee markets. So with that, we're going to talk about what are transactions, what are resources, kind of the mathematical formalism around that, before we can actually talk about how to design pricing rules. And in our definition, a resource is this very general thing of anything that can be metered. So for instance, that could be data blobs, as in like EIP 4844. It could be compute, memory storage. You could go down to the individual opcode levels or bundles of opcodes. You could do specific sequences of opcodes. So for instance, maybe you have a hot slot of memory. So if you if you read from that memory slot multiple times in a row, perhaps that's cheaper than the first time you read it. You could even have multi-core where each compute resource on each different core is priced separately, and so on. You kind of get the idea. These things are very, very general. Anything where I can say a transaction uses a specific amount of this thing is a resource in our framework. So with that, we can then define that, what a transaction consumes in terms of its resources. So a transaction's resource consumption is this vector aj, which is an m vector. And we say that a transaction j consumes essentially aj I, the ith component of that vector, of resource I. Then we can define a vector x. And so this is going to say essentially which transactions are included in a block. So if we have n possible transactions, this might be a mempool, this might be private order flow to a block builder, and so on. Xj is going to be 1 if that transaction is included in the next block, and 0 otherwise. So then we can write the quantity of resources consumed by this particular block very succinctly as just the xj's times the resource consumption of that vector, and we can write that in matrix vector notation as just y equals ax. So y is the resource usage of this block. A is this matrix that just has each column is the vector of resources for transaction j, and xj is this 0, 1 vector that says I include transaction j or I don't include transaction j. Okay, so then there's some natural things that we might want. So for instance, maybe as the network designer, we want to say we have a resource target for each block. So a resource consumption target in Ethereum's case is a one-dimensional market in terms of gas, and that's 15 million gas per block. And then of course we can define a deviation from that target, so that's just ax minus b star. The ith component of this is going to be positive if we're overusing some resource, and it's going to be negative if we're underusing some resource. As a network designer, we also might want to have resource consumption limits. So we don't want people that are, have really beefy machines that are way above the minimum specs to be able to just run the network as fast as they want. So we might say that there's this limit B where we can't include in a particular block more than BI usage of resource I. And then, so now that we've defined this, we can also define prices for each of these resources. So essentially, just resource I costs PI per unit of that resource I use. And we can charge for these resources, like in kind of the EIP 1559 style. When I say charge, this is burned. So nobody gets this, or in some way, essentially this is burned by the network, or the network is kind of what's loosely getting this payment. And so, of course, for some certain transaction, the cost of that transaction is just the dot product of the vector of prices with the vector of resources consumed. The natural question then is, well, how do we determine these prices? And there's a few very natural properties we would want for any pricing mechanism. So one is if the resource consumption is equal to a target, that's probably a good price, at least kind of locally in time. However, if the resource consumption is above our target for a resource I, we'd want to increase the price of PI. The price goes up, less people are going to use it. And similarly, if it's under our particular target, then we want to decrease the price of PI. The price goes down, more people are probably going to submit transactions that use this resource. So there are a lot of update rules that we can come up with that have these properties. One proposal, and this is if you've read the EIP 4844 spec, is this exponential kind of multiplicative update rule. And you can check that essentially it has all the properties I laid out. But the question is this a good update rule? How can we really tell what exactly this update rule is doing? What we're going to introduce is we're going to introduce an optimization problem that these update rules are all implicitly solving. So instead of talking about what's happening with this price update rule, we can talk about what is the objective function of this optimization problem that we're trying to maximize. And that specific objective function of the optimization problem will then imply a price update rule. So in the space of kind of the infinite space of price update rules we could have, instead of saying, oh, is this thing good, is this bad, let's analyze the properties, we instead turn to the optimization problem and say, this is exactly what I want, which I can encode as a maximization problem. And that implies a specific price update rule I want to use. So with that, we'll introduce what we call the resource allocation problem. And the setting for now to introduce this problem is the network designer is omniscient and chooses all the transactions in each block. I know this is an entirely unrealistic assumption, but this will allow us to kind of use the mathematical machinery we want to do, and then we'll relax all this at the end, where we don't actually need to have this assumption whatsoever. So the first thing that we'll introduce, or the first ingredient of the resource allocation problem, is a loss function. And this is going to encode the network designer's unhappiness with the current resource usage. So remember, the resource usage is Y, which comes from the transactions we include in each block. And one kind of silly thing that we could choose is we can say, if we're exactly at our target, our loss is 0. Otherwise, we're infinitely unhappy. So you can think of this as almost like a constraint. We essentially say that we want to be exactly at target. We also might not actually care if we're below our target. And we can say, oh, maybe we have 0 loss until we hit the target, and as soon as any particular resource hits that target, we become infinitely unhappy. Again, these are kind of silly loss functions for the sake of this presentation, but you can imagine much more complicated loss functions that trade off utilization of different resources and kind of are based on data that a network designer collects from usage of the network. The second ingredient we need is we need to say what transactions are allowed. And for that, we introduce the set S, which is a set of binary vectors that essentially say what transactions can we do and what transactions can't we do out of the space of possible transactions. So this might include things like the network constraints. So for instance, we can include a set of transactions that goes over our transaction consumption limit, or our resource consumption limit. But it also can include things like interactions among MEV searchers. So for instance, if there's a particular liquidation, only one searcher is going to be able to get that liquidation in the next block. And so the set S is this very general thing that just says all of these sets of transactions are permissible, and anything not in this set S is not permissible. And then here's the first kind of mathematical sleight of hand that we'll do, is instead of considering S directly, we'll consider this object called the convex hull of S. And in this case, all this means is that we can partially include transactions. We'll see again that we actually don't need this in a bit. But for now, we can think of partially including a transaction as, for instance, if like xj is 1/2, so it's like half including a transaction, which doesn't really make sense. Intuitively, we can think of that as saying we include transaction j in one of the next 2 blocks. Similarly, if it's 1/3, we include transaction j after about 3 blocks or so. And so, at least for now, this is a good intuition for like what this means. Finally, kind of the final ingredient we need is we need some sense of utility function from these transactions. And for this, I'm going to group kind of users and validators together in this like transaction producers. This could also be users, validators, block builders, depends on the specific network. And if transaction J is included, this group of transaction producers will get joint utility QJ. So we almost never know Q in practice, but we'll see very shortly that we actually don't need to, or at least as the network, we don't need to know Q. We can trust that the block builders are the only ones that need to know Q. Okay, so with those 3 ingredients, we can finally define what this resource allocation problem actually is. And that is to maximize the utility of included transactions. Remember, QJ is the utility of transaction J included. X is just this binary vector that says it's included or it's not, minus the loss incurred by the network. And then our constraints here are that the Y, which is the resource usage, comes from the transactions we decide to include, so Y is equal to AX. And then X is in the set of allowable transactions. So that's that set S, which can be very, very complicated or kind of hard to deal with from the network designer's perspective. And this introduces like a number of problems that we have as the network designer if we actually want to solve this resource allocation exactly. First, like we can't decide which transactions are included in the block builders are going to do this, or depending on the network, somebody else is going to do this. We don't know the utilities, so we can't actually even write out what the objective is. We can't compute the objective, much less solve for it. And then, of course, we can't include fractional transactions. But we'll see that we actually don't need to know any of these things, or these aren't constraints, and we'll apply some mathematical tools from convex duality theory. This is the part of the talk that's going to get like very, very math heavy for a bit. And I'd refer to you, in the paper, Guillermo wrote this very nice convex primer at the kind of in one of the appendices, so I'd refer you to that if you have questions on this part of the talk. But we'll go through kind of these very standard tricks that allow us to take this problem that can't be solved in practice by the network designer and turn it into something that can be solved via setting prices. Okay, so duality theory, like roughly, says that instead of having constraints, I relax these to penalties. And one thing that we notice is the network designer really only cares about the resource usage. In some sense, the network designer doesn't care at all about what transactions are included in the block, except insofar as that they imply a specific kind of resource throughput or resource utilization of the network. Builders, of course, and users care about what transactions are included. It's kind of all they care about. Users probably don't care that much about how much resource utilization is used by the network, except insofar as it implies what transactions they can include, how fast they get executed, and so on. So what we're going to do is we're going to decouple the utilization of the network and that of like the transaction producers. And essentially, we're going to set a penalty for violating this constraint. The penalty is going to be exactly the prices. And if we optimally set this penalty, then the dual problem is going to be equal to the original problem. The utilizations are going to be equal, and the objective values are going to be equal. So in some sense, by optimally setting the penalty, we solve the original problem without actually having to know any of the stuff like the utilities, without having to compute kind of what transactions are allowable, and so on. So the dual problem is defined by what's called the dual function, which is this g of p right here. And the dual problem is define the prices p that minimize this dual function. So the dual function kind of has these 2 terms. From before, the prices p are essentially those that penalize violating the constraint y is equal to ax. And so you can think of it as like a per unit penalty, or like kind of a per unit of violation penalty. And the 2 terms here are, the first term is the networks term, which is this conjugate function of L. I guess trust me that this is this kind of very easy object to deal with, and it's inexpensive enough to be computed on chain. The second term, though, is much more complicated. It's the supremum, and like we have the convex Hall of S, and like there's a lot of things going on there. So let's look at that in a little bit more detail. The second term can be rewritten as this maximization problem, which is to maximize the net utility of the transactions included. So that's the utility Q minus the cost for each transaction, which is this A transpose P, subject to X is in the convex Hall of S. And one thing to note that actually if we use S instead of the convex Hall of S, this problem has exactly the same optimal value. So remember before I said that we don't actually need this assumption or kind of need to deal with the convex Hall of S. It's a mathematical sleight of hand that we play to use kind of all the tooling we want to do, but then we can drop or relax that here. And we'll notice that this is actually the exact problem solved by the block producers. So all this says is to include the maximum utility transactions subject to the transactions that the possible transactions I can include. And so, of course, this is what is solved by block producers already. So the network designer in some ways can outsource this problem to those producers. First, before we talk about how to solve this, what do we get at optimality? Well, essentially, if we set prices optimally, and then those prices are used by the block producers to pack the block optimally, we get that y star is equal to ax star, or in other words, that constraint of the original problem, the resource allocation problem, is satisfied exactly. And that y star here satisfies this equation that essentially if we evaluate our loss function, or the gradient of our loss function at y star, we get the prices. So what does that mean? Well, the big key takeaway, or one big key takeaway, is that the optimal prices essentially charge the transaction producers exactly the marginal costs faced by the network. So the marginal costs are the gradient of the loss function evaluated at ax star, evaluated at the resources used by the block, and that's exactly equal to the optimal prices. So in some ways, this is exactly what we want, right? We can think in terms of kind of the marginal cost. We can design the loss function so that it captures kind of the marginal cost of increasing resource usage or decreasing resource usage at a particular usage level, and that is what we should be charging price-wise. Also, these prices are going to incentivize the transaction producers to solve that original problem that we want, which is to maximize the utility of the included transactions minus the loss incurred by the network. So how do we solve, this is like all great, but like how do we actually solve this thing? Well, it turns out we can just compute the gradient. So the gradient is just looking at kind of y star, which is given by that equation, minus a times x star, which is just the resource usage of the block. So all we do is we look at the previous block and can get x star from the previous block. Y star is this thing that's very easy to compute. It comes from that conjugate function. So again, you kind of have to trust me on this one. And then the network can apply its favorite optimization method to run gradient descent, or to run like any type of like fancier thing like LBFGS, but any gradient-based optimization method can be used without having any knowledge of the utilities, without having to solve that block building problem from the network's perspective in this kind of computationally easy way. So kind of to return to the examples I gave at the beginning, we look at that kind of silly loss function. Well, what does that imply as the update rule? It implies something that looks very much like gradient descent, where the gradient is essentially that residual. If we use that slightly modified loss function, where I actually don't care if I'm underutilizing, we get something that looks really similar, except in the second case, I can't have negative prices. And this makes a lot of sense, right? If I don't care about underutilization, the prices are always going to be positive because I'm only going to charge when I'm overutilizing. If I care about underutilization, then I might actually have a negative price where I'm subsidizing people to submit transactions to the network. And that final price update rule that I teased earlier, unfortunately a little bit too complicated to cover in 25 minutes, so I'd refer you to our paper Appendix C. But this falls out of the same framework. So we have some like very simple numerical examples and kind of a toy problem that illustrate this, but essentially the big takeaways are the prices kind of converge pretty quickly to like these set of optimal prices, even starting from like 0 or kind of whatever initialization. Multidimensional prices are always going to be give higher throughput than uniform prices in kind of a network steady state. if we introduce some like distribution shift for the transaction, so this might be something like an NFT mint, then we see the prices will shift accordingly and then kind of come back to a steady state afterwards. And multidimensional prices, again, will achieve higher throughput. And this slide illustrates this quite, I think, like viscerally, where like you can kind of see the dashed lines are the targets, the dotted lines are the limits. And so multidimensional fees go up to that limit for a brief period of time, come right back to the target. With one-dimensional fees, you can get things like oscillatory behavior and kind of undesirable outcomes. So the big conclusion from this talk is really for thinking about pricing in the multidimensional sense, or really any price update rule, you should think about your choice of the objective function rather than thinking about the update rule itself. The choice of objective function through some pretty standard machinery can then yield an optimal price update rule for that specific objective function. So think about the optimization problem, not the algorithm. And thank you. For more information, here's a link to our paper, and then feel free to DM me on Twitter as well. There's a tiny bit of time for questions. Yeah.
Let everyone hear you online.
Okay. Yeah, I didn't quite get why you needed that assumption when transactions can be included partially. Can you elaborate on that?
If you do not have that, the problem is not a convex optimization problem, in which case we don't have the guarantees that strong duality holds. In other words, that the dual problem is equal to the primal problem.
I see.
So we need that essentially to apply the mathematical tooling that we want to do, and I did glaze over that due to time constraints. But that's a great question.
Yeah. Also, you said like you're minimizing the difference between utility of transaction producers and the network fees, right?
No, we are maximizing the utility of transaction producers minus the loss incurred by the network. So one thing is these have to be in the same unit, for instance. So like let's pick your numeraire, and the utility has to be measured in the same unit as the loss. But we're trying to maximize essentially utility that the network provides minus the loss that the network has.
I see. And this, when you by transaction producers, you mean like block builders, right? Not users.
Users and block builders together. So we're grouping these two like into the same unit. This is due to kind of incentive issues when you pull these two apart. And that's also why instead of like the users paying the block builders, when we talk about prices, we're talking about what you burn.
I see.
So if you think about this, it would be like in EIP 1559, there's like some amount that's burned, and then there's some amount there's the tip on top. The tip is kind of what handles like the incentive issues. The amount that's burned is what the network designer cares about because that regulates throughput of the network or resource usage of the network.
I see. So is there like a problem when users and miners or like users and builders collude?
I mean, potentially.
Yeah. Okay.
That's outside the scope of like what we're addressing here. So I would say the collusion problems are like, there's what we're talking about is from the perspective of the network, which kind of like the whole thing is the network cares about how much resources are utilized. Collusion can do bad things for what transactions are included, what don't, and what are not included. And remember, like in this talk, the network doesn't care about what transactions are included at all, except insofar as they imply a specific resource utilization. So this entire talk is talking from like the network's perspective of like how do I essentially achieve a target utilization of the network that maximizes throughput and so on. Like how do I run my network optimally?
I see. Okay. Thank you.
We're going to go here, then we're going to go there. So. Hold up. People need to hear you online. We're on YouTube Live. If people want to tune in, you got mom, dad at home, want to watch this?
Definitely not.
Not safe for work.
Okay, yeah, so this might be a dumb question, but like even with penalties, are there cases where block producers would continue to overutilize even at like higher prices?
Yeah, potentially. I mean, like if you, let's see. So here, for instance, like we overutilize the network, like we're way above target for some number of blocks, maybe like 20 or something like that, where we're hitting that resource limit like exactly. And that's just because, if people are willing to pay a lot to have their transactions go through, you're going to have periods where like the network does spike quite a bit. Prices, of course, then, if you look on this slide, prices keep going up, right? So prices are essentially going to keep going up until that stuff starts to clear. So you can have, and you want to have moments where the network is overutilized relative to the target. And that's why you have a limit. The limit is so that, anyone running like the minimum specs for a full node can still catch up eventually. And the prices ensure that you're not like way over target for too long.
Got it. Are there are there just downsides to kind of long-term price spikes like that? And are there ways to kind of control for that or constrain kind of how long something like that would occur for, or to what extent?
Well, I would say this is exactly this framework is exactly the way to control for that. The downsides are, and the reason you define limits, hard limits, because the downsides are that somebody that's running a minimum spec full node can't catch up with the network. I'd say that's the major downside. Of course, there's congestion and all that stuff. Prices deal with congestion. But at the end of the day, if somebody's willing to pay an infinite amount to get their transaction included, prices can stay high for quite some time.
Right.
So you have to look at historic data and kind of infer from that what it should be. And this is in the design of the loss function.
It should be on.
I'm curious how this research is being implemented or used in the real world. Are you bringing this to all the major layer ones, and kind of is this feeding into some of the thought process that, I don't know, Ethereum Foundation or some of the other layer one foundations or even labs companies are kind of considering as a next sensible iteration?
Yeah, I mean, we've been talking with a number of the layer one teams about this. Different, I guess I am not going to be one that's going to be implementing this, and also we're talking at events like this to publicize this and kind of get feedback on it, and especially because this is we think quite implementable, but it is still at the end of the day it is a math paper, right? So there are some steps where you have to define what are the resources, what should the loss function be. A lot of this is going to be super data driven. So I'm not going while this is very implementable, there are a number of steps to actually get this into production. And we've been talking with a number of teams to kind of talk to them about this work and go from there.
Thanks.
Any other questions?
All right. Theo, thank you very much.
Thank you. Test.
All right. You better be careful over there. Come on now, guys. All right. So continuing on the multidimensional fee structures, I'm going to bring up our next guest. Our next guest is JP Madrigal-Cianci. He is a research and data scientist at the CryptoEcon Lab since July of this past year. He is currently focused on understanding modeling, simulating complex random systems on the Filecoin network, such as gas dynamics. Before joining PL, he simultaneously worked as a research consultant in DeFi for Advanced Blockchain AG and as a postdoc at the École Polytechnique Fédérale de Lausanne Institute in Switzerland. He holds a PhD in mathematics from the same university, where he specialized in uncertainty quantification and inverse problems, a field that lies at the intersection of computational science, engineering, and applied mathematics, and probability. And just so you know, this is a very smart and brilliant man who will show you a lot of mathematical models that will blow your mind. So with that, I will bring on JP.
Hello. Hi, can you guys hear me? Thanks, Mike, for the extremely kind introduction. It's definitely not true, but let's see if I can make this. Okay. Yeah, so welcome, everyone. Welcome to my talk. My name is Juan Pablo Madrigal Cianci. I'm a research scientist at the CryptoEcon Lab. Today, I'll be presenting a talk entitled Gas in the Filecoin Network, Modeling and Uncertainty Quantification. So let's get started. So let's start with a quick overview of the talk. I'll first start describing the concept of gas. How does gas work? What is the relationship between gas and the transaction fee mechanism? What is gas and the EIP 1559 transaction fee mechanism? And how does it relate to demand? I would then present some mathematical models for demand in the Filecoin network. As we will see, these mathematical models depend on a wide variety of parameters that are very difficult or impossible for us to know or to quantify precisely or to know exactly, which brings us to the third part of the talk, which is uncertainty quantification. Uncertainty quantification is a field of mathematics tasked with dealing with these sort of uncertainties in the models. I will then present some toy examples, and I will conclude the talk with some finalizing remarks. Okay, so introduction. What is gas? Well, gas is a measurement of the resources needed for on-chain transactions. So just as you need to put gas in your car to drive it, and your gas consumption will depend on the size of your engine, how fast you're going, etc., you also need to fuel your on-chain transactions or messages by paying gas for them. Furthermore, this computational resource is a finite resource, which means that any given block has a finite amount of messages or transactions that it can include, which implies that at any given epoch, we can only fit so many messages. We can include only so many messages on-chain on an epoch-to-epoch basis. This, in turn, poses two questions. The first one is, how are these resources being paid for? And the second one is, how are these transactions being prioritized? How do we choose which messages go on-chain and which don't? And answering to these two questions is akin to designing what's called a transaction fee mechanism. Now, there are different types of transaction fee mechanisms, but perhaps the most important one for our purposes is the EIP 1559 mechanism, which is the one that's currently being used by the Filecoin network, and is the one that is being used by the Ethereum network since August 2021. Okay, so how does this EIP 1559 mechanism work? Well, each block has a minimum reserve price. This is the minimum that a user has to pay to get their transactions included. This reserve price is called the base fee. The base fee gets adjusted at each epoch according to demand. So if there's a lot of demand for block space, the base fee will increase. If there's not enough demand for block space, the base fee will decrease on the next epoch. And furthermore, in this EIP 1559 setting, users define three quantities. The first one is gas limit, which is an upper bound on the maximum amount of gas that a message is allowed to consume. The second one is gas fee cap, which is an upper bound on the base fee. And the third one is a gas premium, which can be understood as a tip to the miner. Okay, so having defined these three things, the EIP 1559 mechanism works as follows. Here, the users are willing to pay an amount given by max cost, which is equal to gas limit times gas fee cap. Of this amount that the user pays per message, some of it gets burned, and some of it gets sent to the miner as a tip. The amount that gets burned is equal to gas used times base fee. And the reason why we burn is that these distributed systems are a team effort, so even if you didn't get to mine the block, by burning, you decrease the circulating supply, so the value of all the other remaining tokens is a little bit higher, so it sort of benefits all the other participants. And the miners just get a tip for their messages. Of course, miners are incentivized to include the messages with the higher tips. Here, as we can see, all these three factors, they do depend quite, they're very intimately connected with the base fee, right? The maximum cost depends on gas fee cap, which is an upper bound. The gas burned depends explicitly on the base fee, and the tip to the miner as well. So let's understand this base fee a little bit better. So, as I mentioned earlier, this base fee gets adjusted dynamically on an epoch-to-epoch basis according to demand. So if we denote by P the base fee, it gets adjusted again, on an epoch-to-epoch basis, according to this formula here. There's no laser on this, right? Perhaps in words, or a bit more clearly, if the gas used at the current epoch is bigger than the target gas usage, which is usually half of the maximum block size, then the network is congested, and as such, the base fee increases at the next epoch. And conversely, if the gas usage is smaller than the target gas usage, the network is not congested, and as such, the base fee decreases in the next epoch. So, of course, understanding this base fee business and how it relates to this quantity gas usage is quite important for modeling, for decision making, for future planning, etc. However, there is a caveat, and it is that this gas used quantity here, it's a demand-driven and stochastic process. So it's not immediately obvious how to model it. Now, it's worth mentioning that there's a wide body of literature modeling demand in the Ethereum network for this specific EIP 1559 mechanism, just as the one that Theo just presented. However, given that Filecoin and Ethereum are slightly different, it's not immediately obvious whether these models and the implications of these models hold on a one-to-one relation. So, with this in mind, the rest of the talk, has the goal of first understanding gas demand in the Filecoin network, and try to see how and if it differs from the gas demand in the Ethereum network. And the second goal is to develop a probabilistic and data-driven model for gas consumption in the Filecoin network with the hopes that we can use it for planning, for decision-making, etc. So, okay, let's discuss a little bit how to model gas consumption and gas demand in the Filecoin network. And to do that, let's maybe go with a really quick overview of how the Filecoin network works. The Filecoin network is a decentralized storage network. Here, storage providers onboard data, and they present on-chain cryptographic proofs of storing this data on a daily basis. On any given day, they need to provide multiple proofs that they're actually storing this data. It's not that they have to submit one proof a day and that's it. They have to submit multiple proofs throughout the day. This in turn means that the Filecoin storage providers are the users of the Filecoin network. Furthermore, before they start providing the storage, they need to provide some collateral capital as a sort of guarantee that they will keep providing this storage, and in the event that they fail to submit these proofs of storage in time, then they will get some of this capital taken away from them. And it's usually a sizable amount, so of course they would like to avoid this as much as possible. Okay? Now, and here's where it gets interesting, is that at every epoch, these same storage providers are randomly chosen to mine a block and get a block reward. Now, this also implies that the storage providers are miners in the Filecoin network. So they're both users, they have to submit transactions, and they're miners, they get to submit the blocks. And this already creates a subtle but significant difference with respect to Ethereum, right? Because in Ethereum, this difference in agents, right, it's more explicit. So does this difference in, does this duality in Filecoin create a change in demand? And the answer is yes. If we try to examine the utility function of an Ethereum miner and the utility function of a Filecoin miner, we get something that looks like this. So these terms here in black, they represent their expected earnings, like their token inflow. So it is the same for both miners, but for the Filecoin miner, since again they need to provide storage on a continuous basis, they also have these expected gas expenses. Furthermore, while for Ethereum miners, it's generally good to have higher base fees because they will make a little bit more in tips, this is not longer the case for Filecoin miners, because then this term here in pink starts becoming larger and larger, and if the base fee is extremely high, then it might start hurting their business. Okay, so with this in mind, how can we model the demand on for gas in the Filecoin network? Okay, well, to do so, we rely upon some assumptions and observations. The first one is that any individual SP. Okay, sorry. Hi. Hi, can you hear me? Is it on? Hello? Hi? Okay. Okay, yeah, so to do that, okay. Hi. Okay, cool. Yeah, so to model this, this demand of gas in the Filecoin network, we first need to state or rely upon a couple of assumptions and observations. The first one is that each individual SPM will give a value to the messages according to this formula, which is essentially their expected rewards, their expected fees, minus their expected expenses, minus their OPEX, this term in orange, which are their operational expenses. Of course, this is going to vary widely between miners. It's not the same as to pay for electricity, say, in Colombia than to pay it in Switzerland. Sorry. The second assumption is that at the minimum price, which currently is set to 10 to the negative 16 fil per gas unit, all SPs are happy to submit whatever messages they need to submit. And the probability of submitting, or the proportion of the messages that they submit, decreases as this valuation decreases. The third and fourth assumption are a bit technical. They can be relaxed a little bit, but they say that the first one is that the timescales that we consider are small enough such that the relative power of the miners in the network doesn't change much, and that the average gas used by an SP is proportional to their network power. Furthermore, we assume that the price is in general multi-scale, meaning that it can take several orders of magnitude. It can vary between several orders of magnitude, as is the case. The sixth assumption is a bit more mathematical and a bit more abstract, but we assume that the number of messages that arrive at the mempool to be included at any given epoch follow a random process that depends on demand, that in turn depends on price. This is a little bit more abstract, but it goes in line with what other works in this field have been done. And lastly, we assume that we understand well the gas cost of messages, that we know how much a message costs. Okay, so with this in mind, we can propose some demand curves for the miners, as the one that we have here. This is based on a family of functions that are called skull survival functions, and we have that here. Demand is given by this orange term D, which is the demand of a miner whenever the base fee is at the lowest, times this S function here in purple, which is a survival function, meaning a function that continuously decreases. Furthermore, given this observation that this is a multi-scale function, we have that this survival function takes several orders of magnitude. It decreases very slowly, but then once we're reaching the limit of the base fee that would make the valuation of a miner 0, it decreases quite rapidly. Furthermore, here I am trying to make it very explicit that this demand function is very unique to each individual miner, because every individual miner will have different needs. So that's why I have this subscript M. And in order to make more explicit that this demand function varies between miner and miner, I'm including these parameters A and B. A is the decay rate, so like how sharp is this shoulder on the function, and B, which is the threshold at which this function hits its half maximum. Okay, so we have a parametric model for demand, that's fine. However, we know that this model is by design probabilistic, and it's extremely miner dependent. It is very sensitive to each individual choice of A, B, and D, to these parameters. And these parameters, they're not very easy to know precisely because, again, they depend on every miner, so unless you literally knew every single miner, you wouldn't be able to estimate or to know what each of these parameters. So what can we do in this case? Well, this is where uncertainty quantification comes into play. So with that, we move on to the third part of the talk, which is UQ. So what is uncertainty quantification? What is UQ? Well, UQ is the field of math tasked with characterizing and quantifying the uncertainties that arise on systems in science and engineering using mathematical models and simulations. The goal of UQ is typically to improve decision-making and risk management in these domains. Okay. UQ works by identifying, propagating, and reducing uncertainties that can occur due to input parameter uncertainties, model structure uncertainties, and numerical methods. In our particular case, the source of our uncertainties comes from the input parameters. And in order to do so, very common UQ techniques include sensitivity analysis, trying to understand how sensitive an output is to a random input, calibration, validation, and uncertainty propagation. For the purposes of this talk, we'll focus mostly on uncertainty propagation due to parameter uncertainty. So how does this work? We have an uncertain parameter that I'm denoting here by U, we have a known distribution of the uncertainty of these parameters that I'm denoting here by mu PR, sorry. So we know this distribution, and given these two things, giving a mathematical model of the system that we want to model, that I'm denoting here by F, and some observable quantity of interest that I'm denoting here by Q of I. If we have these four things, we want to see how this uncertainty sort of moves from the input to the output. We want to quantify this purple distribution, this purple bump, given this orange distribution that we can kind of estimate. And the way of doing so is extremely simple, and it's extremely powerful, and it's based on a mathematical methodology that is called Monte Carlo. Essentially, what you need to do is to repeat the following steps many, many times. You sample input parameter, you propagate this uncertainty through the model. So you sample U, you evaluate F of U, and you evaluate the quantity of interest at that U. You store your sample, and then you repeat this process many, many, many times. By doing this, you will be able to compute estimates and to compute error estimates as well. Monte Carlo has super nice mathematical properties, so by just running these simulations, you'll be able to get a wealth of information. Furthermore, it's extremely simple and it is extremely powerful. However, there's a caveat, and it is that one needs to be very careful or very sure in modeling this uncertainty, this input uncertainty, because if you're putting rubbish in your model, you'll be getting rubbish out, as with all models. Okay, in our setting, potential quantities of interest could be, for example, the expected maximum amount of gas burnt, the probability of exceeding a given base fee for a given amount of time, the average base fee over a day or something, and so on and so forth. And potential sources of uncertainty can be, for example, in our setting, the maximum demand, the miner threshold, and the decay rate. Okay, so let's put it all together. Let's put this on a toy example with an agent-based model with some uncertainty quantification. So our goal here is to simulate gas consumption in the Filecoin network using an agent-based model and estimate some very simple toy quantities of interest and visualize their output distribution. And again, it's just to make the point that we need to take these things into account. Okay, so our model consists of exactly one agent who is a miner that is equipped with a randomized demand function such as the one that we have here. And instead of the first demand graph that I showed you, here we have different realizations of this demand path. So instead of having exactly one, you can take, the model takes whichever one of these light gray lines that we have there. Okay? Furthermore, our simulation environment works as follows. We do Monte Carlo on the following procedure. So we do, it's a bit computationally heavy, but it's important to get these things right. So at every epoch of the simulation, we simulate for 1 day worth of data, so 2,880 epochs. At every epoch, M messages arrive to the mempool, each with their base fee, miner tip, and gas limit. This number of messages M is a sample from a Poisson distribution that depends on the current level of demand as defined by this function here. The miner looks at the mempool and packs blocks on a greedy way, like they pack the block to the maximum level up until the base fee, like whenever the base fee is lower than BM, because at that point, if the base fee increased more, then they will start hurting them. And then, then the base fee gets adjusted according to the gas usage, and we repeat this many, many times. Now, these parameters here, the M and the ranges of A and B, one can get by doing some data analysis or doing some mathematical analysis, but they can be estimated, and these ranges can be estimated as well. So if we do that, we can get some simple results here. So here on the top, what is that left? We have the realizations of the demand function, just so it's a bit more clear. Again, the point here is that instead of just running a simulation with one exact curve, you can do it, you run it with multiple curves, and it sort of captures a more robust behavior. Here on the top right, we have different realizations of the base fee. As we can see, some of them can go a little bit high up, some of them can go a little bit down, but most of them stay within a range. And here at the top, at the bottom, sorry, we have the histograms of the gas usage of the blocks. On one side, we have the simulated data, and on the other side, we have real data. And of course, these histograms they don't look exactly right, but with this extremely simple model, we are able to capture things such as having a mean of this distribution to be centered around more or less the target gas usage. Furthermore, we can also estimate things such as the distribution of the amount of tokens burned. So if we were interested to measure how many more tokens we would burn on the network, if we were to produce a change, we could apply this methodology and see the distribution of that and try to understand the average and the mean of that. Furthermore, we can compute arbitrary quantities of interest. So I have two simple ones here. The first one is to understand the probability of having a mean base fee larger than the initial base fee, so which ends up to be around 7%. And the second quantity of interest is to the probability of having the base fee go below 10 to the negative 15, given that it started at 10 to the negative 10. And this we can estimate to be around 1% with, of course, its own error estimate. Okay, so to finalize real quick, quick summary. Here we introduced gas, we introduced the EIP 1559 mechanism, we explain how it works in Filecoin, and we explain how this mechanism depends on gas demand. We also presented the key differences between demand in the Ethereum network and the Filecoin network, and we proposed some parametric models for demand based on a set of very simple assumptions or observations. It is worth mentioning, though, that these models, they're very sensitive, or they depend on the input parameters, so one needs to be careful when modeling the input to these models. And as conclusions, we have that, well, these demand models are subject to several sources of uncertainty, and if there is a take-home message from this talk, is to, if you're a modeler or if you're someone who works with simulations, is to please try to always include these sources of uncertainty. If this is something that it's interesting to you or that you would like to work more on, talk to me or talk to Mike. There are mathematical frameworks to handle these uncertainties, and it's a well-studied field of math. And of course, again, as I mentioned, you need to incorporate expert information to construct your priors. And something that I didn't mention is that you can use very similar techniques to understand things as sensitivity, such things like how does an output change with respect to small changes in an input, for calibration, perturbation, and stuff like that. And with that, I finish. Thank you so much.
And we have time for questions, Q&A. Q&A for JP. Right over here.
Hi, so I was wondering if there are any known or easily explainable ways to like know how good your uncertainty distributions are. Like you said, kind of like the inputs to the model. Is there like a well-defined way to measure that, or is it just you have to kind of?
That's a really good question. It depends a lot. You need to incorporate a lot of expert information. You know, like it's pretty multidisciplinary, but it's also a bit of hyperparameter tuning. So you can try to fit these distributions that. Like you can try to always find the best possible input, but yeah, it's a tricky problem. So it's more common and easier to do it a little bit more analytical, for sure. But that's a great question. Yeah, thanks.
I saw a hand in the front. Oh, there it is.
Hey, so you make these 7 assumptions at the beginning, but then afterwards just... Sorry, can you hear me?
Barely.
A little bit? Is this better?
That's better.
All right, there we go. So you make these 7 assumptions at the beginning.
Yeah.
Right? 7, I think. And then afterwards you go and just give a concrete model, which is just, look, here's this parametric family. Let's just take that as our basis. So I guess my first question is, have you said anything more by making these assumptions, or should you just take the model as a given?
So the model is made to, in a way, satisfy these assumptions. Now, some of them are a bit technical that I should have probably removed them, and they are kind of to facilitate the modeling of the distribution of DM, AB, and AM, and BM. But yeah, you can. I think the strongest assumption is the first one, which that you give a value to the messages and that this value decays with the price. But even then, I think it's quite a normal assumption, and I think it's fairly common in that field.
I mean, so I guess what I'm confused about here is you give these 7 assumptions, right? And then you just give one, like a specific choice of family of functions, right? So like, why make these 7 assumptions in the first place when you can just give the concrete family? Because, you don't, I don't know, do you give like, like you could imagine there's many other families of functions that fit these 7 assumptions.
Of course,
right?
yeah, you can come up with whatever family of functions for which many of these assumptions are that you can use here, and that for which these assumptions are satisfied if you were to implement them. For sure, that's not a. It's not a physical law, right? It's not that all demand has this form. It's more like this demand sort of matches what we observe.
Okay, thanks.
Additional questions? I saw another hand a second ago. Was that you?
I think someone at the back.
There we are. I got him.
This might be slightly beyond the scope, but why did you use EIP 1559 as the base case?
Sorry, I couldn't hear you.
This might be slightly beyond the scope, but why did you use EIP 1559 as the base case?
Is the question, why did I use
EIP
1559 as the base transaction fee mechanism?
As the base case.
Sorry, Mike?
As the base case.
Because it's shared by both Filecoin and Ethereum, and I work for PL, so it's of interest for us. But of course, if you were to use different transaction fee mechanisms, like first price auctions or whatever, then you would have to think this stuff a little bit differently. I don't know if that answers your question.
Any additional questions for JP? JP, thank you very much.
Thanks, guys.
Thank you. Awesome. Thank you.
All right, ladies and gentlemen, can you hear me? Awesome, so that was super insightful. Now we're gonna get out of the multidimensional phase a little bit with our next guest in Connor O'Day. Connor is the revenue lead within the team of Gitcoin DAO. Connor's background is in economics and computer science. He began working at Consensus in 2015, followed by Gitcoin in 2019. At Gitcoin, he initially led partnerships and developer community growth with the virtual hackathons team, and following the launch of the Gitcoin DAO, transitioned to the public goods funding workstream, managing ecosystem partnerships and program strategy. He's excited about increasing the adoption of the quadratic funding mechanism and experimenting with it in new and unique ways. And personally, Connor and I were both at Consensus back in the heyday of 2017, 2018, and we had a blast together. I always loved his insights, I always loved his knowledge, and I think you guys will all get a great insight into what quadratic funding was, is, and how it will impact us in the future. So with that, Connor O'Day. Oh, yours, brother. What was that?
I'm just going to scooch this back ever so slightly. Okay. Cool. Yeah, let's do it. Hello, hello. Can you guys hear me? All right, we're coming through. Awesome. So thank you for having me. Really excited to be here. Really hyped to talk about quadratic funding as usual. So this talk's titled Quadratic Funding, Past, Present, Future. We've had a few years now to kind of experiment and iterate on the mechanism, and I think we're working on some exciting things for the next couple months, years, and we'll really expand on what it can be used for. So yeah, let's dive in. So again, I'm Connor. I'm at the Gitcoin DAO. I work on the public goods funding work stream, and we fund public goods. So the past for quadratic funding, how did we get here? It's only 4 years old, so the paper came out in 2018 that initially pitched it, and it's kind of achieved great things for a mechanism that's so new. So first, what is QF, or WTF is QF? I like that saying. There's a website that explains it really well that's called that. But it is basically the mathematical optimal way to fund public goods in a democratic community. So it was first proposed by Vitalik Buterin, Glenn Whale, and Zoe Hitzig. And they essentially expanded on the idea of quadratic voting, but added this financial component to it, which we'll look at in a second. But the way we use it is we raise a matching pool of funds. We let communities donate to, or individuals donate to projects and communities they want to support. And then there's matching allocations that are calculated off of those donations that it really values the number of unique donors over the actual size of donations. So again, QF was always kind of derived from quadratic voting, and quadratic voting sort of has been around a long time, like even before crypto and Web3. This was always kind of a concept, and it tackles a similar problem, and is often kind of used in this context of buying votes. So there's always sort of a financial aspect to it. And so with quadratic voting, the amount of influence you purchase is basically proportional to how much you care. And if you look at this image, in a $1 one vote system, it's dominated by people with the most capital. One person, one vote is dominated by people. And so somewhere in the middle, you get quadratic voting or quadratic funding, where it weighs both the strength of preferences, but doesn't put too much weight on capital or how much influence someone has. And so as a quick example, say we had 2 grants and we had a $200 matching pool. If you got a $100 donation from one person to one grant, and then $10 donations to the other grant, with quadratic funding, grant 1 would get about $20, and grant 2 would get $180. With traditional one-to-one matching, that would just be 100 and 100. And so you can kind of see there really the strength of the number of unique donors. And down below, this is kind of what the end user would see as they're donating. And I really like this feature of quadratic funding, that you sort of can visualize and see your impact as you're making a donation. And you can kind of see how the matching almost scales up, but like logarithmically on this curve. So you can see, $1 might make a huge impact compared to, $10 will make a bigger impact, but that will be kind of dampened as you increase that amount. And so how does that actually work? In plain English, you take the square root of every donation, you sum all of those square roots, and then you take the square of that final amount. And this has always sort of confused me, like the mathematical formula, doesn't make a lot of sense. But I really like this image here, and once you kind of fully grasp it, it starts to make sense. And so you can look at the green squares here. Each green square is one contribution. And so if you imagine the square root of that, right, is just the length of one side of that square. And then so you're summing all of those contributions, and at the end you square that, and that's the total amount of funding. And so in this case, that's the entire square. The yellow would be matching, and the green, or I guess it looks kind of white on here, would be the individual donations. And it's worth noting this sort of assumes that there's an unlimited pool of matching, because what you'll get is some final amount that every grant should get matched. In reality, we sort of have fixed size pools, and so we take these final results and then we have to basically reduce it down in like the same ratio that they are getting their initial results, because we don't have unlimited capital. And so it's a bit of a tweak on like the pure math, but it's sort of how we've implemented it and how it works in practice. So we've been doing this at Gitcoin now for 4 years. The first quadratic funding round we did in 2019 had 200 contributions, and 38K total was distributed. I think there was a 25K matching pool and 13K in user donations, up to one of the most recent rounds, grants round 14. We had, I think, about a $3 million matching pool, and over $2 million was donated, with 600,000 contributions total. And so you can kind of see visualized here the networks in 3D of all of these donations and grants, which is pretty cool. And on the graph there, you can see sort of the adoption has increased exponentially. And we've changed kind of how it works a lot. So we started off with one single main pool. We've then sort of iterated on that with having separate categories that were mutually exclusive, so you can only be in one. And then we started running these kind of overlapping rounds where you could be in multiple categories and eligible for matching from multiple pools at once. We've implemented pairwise bounding, which is basically a collusion deterrent. And so we're detecting similar patterns of donations from users. And so it's kind of visualized here in this image. But if you see there's a big cluster of a group of people that are all donating to the same certain set of grants, their influence will be dampened a bit to sort of prevent collusion and Sybil attacks, which we'll talk about more. There was one round where we tried negative voting, where you could actually vote a project down by donating, and you'd essentially be donating to everyone else. But that got really kind of ruffled some feathers. People didn't like that, so we took that away. We played around with like conviction voting, where you can stake on a grant, and that affects how it's shown in the UI. We've implemented matching caps now, so there's a certain percentage of the matching pool that a grant can make total, and then it's kind of cut off at that point. And as well as trust bonuses, Sybil scores, so you verifying your identity, proving you're a real person, to get sort of an increased bonus to your donation in the match. And we've sort of experimented in a lot of places. So we kind of started out just focusing on open source software, kind of specifically in the Web3 world. But we've started running what we call ecosystem rounds now. So we've done some with like Polygon, ENS, Protocol Labs. We've done one for Ethereum infrastructure and many others. I think we've done over 20 unique ecosystem rounds total, and I think like 40 something total. We've been doing cause rounds, which are what we kind of call these more thematic focused grant rounds, where it's usually focused on something in the real world that's not necessarily Web3. So we've done some for climate solutions, diversity and inclusion, advocacy, which is focused on like lobbying and legal policy. And then we've done a bunch of what we call kind of local rounds, where we've done, usually smaller matching pools for, we did one for Oakland that was focused on these charities that are focused on youth restorative justice. We did a Greater China matching pool for Chinese projects. And actually, Downtown Stimulus was sort of this experiment during COVID that we did to fund small businesses in Boulder, Colorado. And this was a total like Web 2 QF implementation. You could use a credit card, and that was sort of this fun local experiment that we did here. And so I think local rounds are really interesting because basically we're all sort of experts on like what's right in front of us and what's in our own communities. And I would say that like it doesn't have to be geographically local, right? It could be digitally local, or like ways you gather, whether it's in person or online. But it's all about kind of bringing together smaller communities that maybe these aren't fully public goods that everyone benefits from, but it's about certain communities getting together to fund their shared needs. So it's all coordination, and Ethereum has sort of been this tool that has enabled what we've built with quadratic funding and public goods funding. And at the end of the day, Ethereum is just this global coordination tool that we're trying to figure out how best to use it. So the present. What are we doing? How did we even get here? What is here? So that was kind of some of the history, and I'm going to talk a bit about what's going on right now. So far, Gitcoin Grants has distributed over $50 million. We've had over 270,000 donors and over almost 4,000 grants funded in total, and that's almost 4 million unique donations in total. So this has been sort of a cumulative growth over the last 4 years. And this kind of all happened on our current or old, more centralized grants platform, which I'll talk about in a second. But I want to call out too, it's not just Gitcoin that is doing this. There's a ton of other projects that have now emerged that are experimenting with quadratic funding, quadratic voting, just public goods funding in general. I think worth calling out Optimism, Pool Together, CLR Fund, Giveth, ENS, Juicebox. And there's many, many more that are starting to experiment with this, which is what we love to see. So as we kind of talked about, quadratic funding has sort of always been focused on public goods. And what are public goods? It's basically a non-excludable, non-rivalrous good that might be clean air, open source software, privacy, the internet. And I think what we've noticed is although we started very focused on public goods, we've sort of expanded to focusing on, not just focusing, but, applying QF to these many other places. And so it's not really, regenerative finance is not limited to just public goods. There's all types of goods that can benefit from this. And this is a conversation that I think has kind of really increased over the last year, is that it's much more of a gradient. And, I had some fun with word art here, but this recent paper from Glenn and Vitalik, so 2 of the 3 initial quadratic funding paper authors, focuses on soul-bound tokens, SBTs a lot, but it's a good discussion of like the nuances of public goods and the associated networks or models that best serve them. And it specifically kind of calls out this idea of partial and plural shared goods, which I thought was really interesting. And there's also been a lot of other just, like brainstorming and idea throwing out there on Twitter and all these other places that we could expand this model of public goods. So we'll see, we have this idea of like community goods, semi-private goods, network goods, semi-excludable goods. And as we think about applying QF to many different geographies and smaller and local communities, it might not always be public goods, but there's still value to using this mechanism to coordinate as a group of people. So the growing pains, though. So as we've kind of grown quadratic funding through Gitcoin pretty significantly, I'd say the biggest hurdle and barrier right now is Sybil attacks. And a Sybil attack is essentially one person or bot making a ton of accounts and using that to kind of game the system. And so you can imagine, if one person can make a grant and then donate to their own grant 100 times from 100 different accounts, they can basically steal, a big part of the matching pool. It really just makes the mechanism totally useless. And we've kind of found that it's this infinite game of red team versus blue team, where the bots and the attackers are getting more sophisticated, and so we have to increase our ability to detect that and to dampen their impact. And so I think what we've also seen a huge increase of is airdrop farmers, and so as we've seen larger airdrops that have included Gitcoin or public goods funders, people see that. They recognize it, and all of a sudden they want to, kind of farm a bunch of accounts that would be potentially eligible for future airdrops. And then there's the people that are, just donating to themselves under multiple accounts or just colluding in groups. And we've also seen a lot of, fraudulent grants kind of pop up that are either impersonating a legitimate project or basically a grant emulation is what we call it, where they just make up a project. They make it look sort of real, but there's really nothing going on behind the scenes. And so after every round, we have this extensive fraud report where you look at how many donors are suspected Sybils, what the impact that is on the final matching and how that changes. And yeah, so over the last few rounds, the Gitcoin fraud defense team has stopped over $3 million in fraudulent funding that would have went to fake projects or Sybil attack grants. And they have been calculating this fraud tax, which is basically the delta between how funds would be allocated if we did no Sybil detection and how they are actually allocated after we remove these attacks. And there's a lot of different signals. You can look at on-chain signals, connections between wallets, similar patterns, and it's not foolproof. It's kind of, a growing. It's more of an art than a science, I would say. But we're really trying to work on our automation of it and kind of like data science capabilities to detect these things. So like I sort of mentioned before, we have our old Gitcoin grants platform that many people are likely familiar with, or maybe you're not, but it's existed for a while, and it's what you would have used if you've used Gitcoin in the past. And it was centralized, right? So it kind of had to be that way. Without decentralized identity, like there's really no way to prevent Sybil attacks at a large scale. And of course, we can't really go to governance on every decision around approving grants or disputes and appeals. So we've sort of handled this as a team, as a DAO, in a fairly centralized way. But basically, what we've been building for the last year is a grants protocol, a decentralized, permissionless, quadratic funding platform. And that's sort of what we've just recently launched. We just ran our first, what we called alpha rounds on the protocol. And we're going to be doing a lot more there, pretty much moving the whole grant program over to the new protocol. But more importantly, this is going to be a protocol that is open for anyone to use in a permissionless way. So you don't need to go through Gitcoin to run a QF round. You can build your own extensions and features and UIs and tools on top of it. And it'll be open for anyone to use. Right now we can deploy to any EVM chain, and in the future possibly other chains as well. So this is kind of where we're going. And the difficult part with that is again, identity and Sybil attacks. So like I said, on the centralized platform, we had to monitor all of this ourselves. Without that, we don't necessarily have IP address data, email addresses, and so we're looking at much more on-chain data. And what we need to do going forward is, funnel this energy of airdrop farming and Sybil attacking into something that we can monitor and prevent, while at the same time getting them to fund public goods without them even meaning to or knowing they're doing it. So the steps we're taking to get there, first and foremost, is something called Gitcoin Passport. It's basically a collection of a bunch of different Web3 identity systems and also Web3 identity systems that you can get verifiable credentials or stamps on your passport that basically prove you took these actions. You have this much on-chain activity. You have these Web2 social accounts. And by verifying all of these things in a privacy-preserving way, you can essentially prove your personhood without having to really give up any personal details. So this is something we're still sort of experimenting with. We used it for this initial alpha round I just mentioned. And going from that, we'll be doing a lot more experiments, and it's also open for other projects to integrate and use, and so we're sort of hoping that this will become a more widespread Web3 identity system that projects can share, and over the years will be built out in a significant way. And as well, going forward, like I said, we're sort of moving from this more centralized platform to a decentralized protocol, which is great and in the spirit of Web3 and crypto, but the other goal we have is to, bring QF to the masses, and so make it easy enough for, your grandma to use it. Make it so you don't necessarily have people needing to custody their own private keys and all of that. And so it's sort of a balance here between, building a fully smart contract-based protocol and at the same time, making it easy for anyone to use. And so it's a bit of a bounce. I think right now, again, Web3 in general, the user experience is improving. It's getting there, but it's still a long way away. But we're hoping, once we have this protocol fully live, we can then sort of focus on usability and making it easy for anyone to sort of plug into and use. And further extensions. So there's a lot of other experiments going on with QF and just public goods funding. I think Optimism notably has been doing what they call retroactive public goods funding. They don't want to necessarily fund things that are going to be built in the future. They want to reward things that have already been built. And it's sort of expert driven. It's typically whitelisted, so that reduces the threat of Sybil attacks, but it's also less inclusive. But the idea here is that if we can set this precedent that if you build good things that are public goods, that you will be rewarded in the future, we could actually be incentivizing, investors and early stage funders to invest in building public goods. Kind of from the start. So it takes this sort of opposite approach. Things like dominance assurance contracts. This is this idea where if you could donate to support some public good, but if it doesn't reach a certain threshold, all that money is returned to the donors, as well as some bonus on top of it. So basically, you either get the public good that you want to fund, or you make a profit. And so the goal with that would be to sort of solve the free rider problem of people not wanting to donate to public goods, because it sort of skews the incentives a bit. And then we have MACI, which is minimal anti-collusion infrastructure, and that's all about privacy. So it helps to avoid collusion and vote buying by making it so no one can cryptographically prove the way they donated or how they donated. So the results can be more credible, more friendly to the honest community, but you have less kind of visibility, and there's some other more technical aspects of it that make it a little more difficult to implement. And so, you know, we've been doing this for Web3 public goods, you know, some of these cause rounds in the real world, but I'd like to think that QF could be used for, you know, many other things that aren't necessarily public goods. So you could imagine, you know, a private university trying to distribute their endowment, a group of friends deciding what restaurant they want to go to. We haven't really tried that one, but I think it could work. You know, country clubs, corporations prioritizing budgets, homeowners associations funding whatever they fund. There's a ton of ways I think that we could experiment with this with both public and private communities, both at a geographic scale and at a very local scale. We could think about government spending. I mean, this is probably far-fetched, but imagine if you had some portion of your tax dollars that you could actually vote with your money on how to allocate it, and by kind of donating to, you know, different initiatives, I imagine we'd get a lot more social services and, you know, public parks and things like that, and less, you know, military, you know, machines and, you know, drones and whatever else. Or just locally in your neighborhood, you could think about, you know, running a QF pool, and you get the added benefit of raising more money through donations, as well as having this pool and getting these signals from the community on what they want to fund. So yeah, this is sort of our goal right now, to reach this like coordination maximalism, both within tiny communities and with the global communities. And I think we'll have to experiment with many different like flavors of QF to figure out what's best, and what works for one group might not work for another group. But that's our goal with the protocol, is to essentially enable anyone to use it in their own way. And almost done here. I know we're running short on time. I wanted to throw this in here. This actually just launched today, and so I threw this in last minute. But we just released this NFT collection with MetaLabel. That is the initial quadratic funding white paper, along with a few other papers that have been written by people at Gitcoin, people at the EF, that you can buy this NFT of the open edition that will then go to help fund public goods. And then there's also physical editions that come with physical pieces of the white paper for quadratic funding signed by all three authors. So if you look up MetaLabel Gitcoin, you'll see that. That's coming out. Well, it's out now. We'll be announcing it, I think, tomorrow, sort of at ETH Denver. And yeah, that's it. So at Gitcoin, we want you to help us fund what matters. You're invited to join and help us test the new protocol. And we want to hear what you guys want to fund, what communities you think would benefit from this, and much more. So thank you very much. And now I'm open for questions.
Questions from the crowd.
I think you got one over here.
Can you hear me?
Yeah.
What's the typical dollar figure that you see for people organizing the grants? 25,000, 50,000?
For the matching pools,
yes,
or for what?
For the
grants?
matching, yeah.
Yeah, so I mean, it very much depends. Like, so for some of those ecosystem rounds, we've done as small as 25K, 50K. For some of the local rounds, it was like 15K. And then, you know, some of our larger pools have been 500,000, $1 million. So it certainly varies a lot. Typically, it's always pegged to USD, but now with the protocol as well, you could do it in some native token, so it doesn't necessarily need to be pegged to USD either. But it really varies, because some rounds will have 800 eligible grantees, and some rounds have, you know, 10 or 15. So it sort of depends on the scope.
I have a question, actually. So you mentioned a lot about Sybil resistance, and I'm curious if you have any solutions, ideas of how you could prevent that. Is it identity-based solutions, products, things like that that could help out? I'm curious.
Yeah, exactly. So, I mean, it's all identity systems. Right now, our identity systems are super fragmented on the internet, right? We have all these Web 2 social profiles. We have some on-chain, activities, and then we have our meat space, government-issued ID or whatever it is. And basically, we're hoping by aggregating a lot of this data, we can create what we're calling a Web3 passport, where, in a similar way that like ZK technology works, you can basically prove that you're a unique human, you have all these different profiles, you have many years of activity without having to sort of give up that data and having all of it live on chain. And so, yeah, I mean, I think it's going to take time. It just takes time to build up histories and like have all this data, live in a central place. But yeah, that our whole plan is around this is Passport, and we're hoping that as other projects integrate it, other DAOs use it, it'll just build out more of this rich set of data.
Thank you. Any other questions for Connor? Thank you very much.
Cool. Thank you guys very much. Appreciate it.
Thank you, buddy. Appreciate you.
I was on mute. How's everyone doing today? Can we get a whoop? Are people paying attention in the back? Are we just having conversations? No, I'm just kidding. Thank you everyone for joining another exciting presentation. And next we have Robert Liefke. Robert is the co-founder. Oh, give me 1 second. Got to show his face so you know what he looks like. Robert is the co-founder of Numion, a company building innovative automated market-making technology to make on-chain markets liquid and accessible to all. Now, Robert and I actually met in New York about a couple months ago, and I found his perspective on crypto markets and everything DeFi so innovative, so exciting, that I think you guys will learn a lot from him today as well. So with that, here comes Robert.
Sweet. Yeah, thanks for the introduction, Mike. Nice. Can you guys hear me okay in the back? All right, great. Just press this. All right, perfect. So today, I'm going to be talking about, or I'm going to be giving a brief introduction to replicating market makers. I work with Kyle on Numion, and I'm very excited to do it. Perfect. So a little bit of background on constant function market makers. So blockchains have, unfortunately, this computational limit, right? So you've seen a lot of these automated market makers flourish in a blockchain environment. So, Uniswap is primarily used as the go-to mechanism for decentralized exchange. And usually, these automated market makers have been kind of seen as these buyers and sellers on a blockchain with a very fixed strategy. You have this trading function that essentially dictates the trade, and it's essentially a rule that says, is this trade proposal accepted or not at some definitive price? But Angeris and Chitra, Angeris being actually right here in the audience, show that there was a different way of looking at replicating market makers. You could actually see that there's this duality between the portfolio value and this trading function of a constant function market maker. And what's really cool about that is you can now look at a constant function market maker not just as a mechanism for a decentralized exchange, but you can actually look at it as this sort of portfolio manager that tries to optimize a portfolio to some desired weight, which is really, really cool, using arbitrageurs. Now, looking at this replicating market makers paper, we saw that you can essentially pick any sort of desired payoff as long as it's consistent and turn it into a trading function. So this type of idea of replicating market makers actually predates blockchain. First, this idea of portfolio replication was proposed by Durman, who's this professor at Columbia. He sort of described this way of constructing an exotic options portfolio and described it as a way of minimizing the dynamic hedging costs associated with constructing with these exotic options. And that's really cool because blockchains have these computational limits, so it becomes really, really difficult to dynamically hedge any sort of option instrument on chain. We see the implications for this portfolio replication to be tremendous in blockchain. As maybe many of you guys know, Black-Scholes model or computing any sort of derivative model on chain is incredibly expensive. It's computationally expensive to do, and so on. And so if you can offload the hedging costs associated with creating some sort of derivative portfolio to these arbitrageurs, you can really reduce the overall cost of constructing these derivatives on chain. And then the really, really cool part, as many things are on chain, you can actually fractionalize these automated market makers into individual LP shares. And these LP shares, depending on sort of how you construct them, they can be fungible. And the LP shares represent a fungible claim to a derivative payoff. So all of a sudden, you can create these truly fungible derivatives on the blockchain through these LP shares. So LP arbitrage dynamics are really interesting. You kind of see this zero-sum game between the LPs and arbitrageurs that was also first introduced in the Replicating Market Makers paper. There is some interesting dynamics there due to its path independence. And you can also see that LP profits are realized inversely to arbitrageurs. So in essence, if an arbitrageur's payoff is maximized, the LP payoff is minimized. And then what's really cool about that too is you can create different types of constant function market makers or different types of invariants, like the log constant function market maker, where if you delta hedge a log contract, you're actually getting the payoff of a variance swap, which is really, really cool. And you have these arbitrageurs that are constantly trading against the portfolio to rebalance the prices. This is referring to the dynamic hedging or minimizing the dynamic hedging cost, as mentioned prior. So why are we excited about replicating market makers? So there's this really cool derivative called squeezed. It's been kind of a meme, but what it really is, it's effectively a power perpetual, something that allows you to get this quadratic payoff on the blockchain, this convexity that a lot of people and traders strive for. Actually, in the replicating monotonic payoff paper that followed the replicating market maker paper, the invariant for this was introduced. You kind of see the invariant right here on the board. It's super elegant and simple here. And we thought, you can essentially increase the order or the momentums as they are to not just do quadratic payoffs, but kind of go up in momentum. So we looked at this paper, we saw this invariant, we saw this very simple way to create these convexity instruments on the blockchain. So we decided, okay, let's go ahead and implement this. So the power market maker is essentially a protocol implementation of the capped power invariance. It's made possible by the lending and borrowing of LP shares. So you essentially have these LP shares that have this concavity to them, or this very specific derivative payoff. And if you over-leverage these LP shares through these lending and borrow mechanisms, you can actually get this convexity that you naturally find in traditional finance. So this is really beautiful because you get this replication of convex payoffs, which is great. And here's the portfolio value, as you can see. And on to the next slide. So here's a chart for people that like to visualize these payoffs. So the green line kind of represents the LP share or the portfolio value, which is really, really interesting. You kind of see this sort of be similar to a covered call strategy or the portfolio value of something like a Uniswap LP share, where you have this sort of concavity to it towards the end of the payoff. But then really unique to these power tokens, if you're going long, is this kind of convexity, as you can see. And in theory, you could probably match the convexity with the concavity of a Uniswap LP share to sort of minimize the price movements or the volatility associated with that option effectively. So yeah, we're pretty damn excited about power tokens. So power tokens in its current form offers something really cool, and that's constant squared leverage with no liquidations. When you think about getting leverage on any sort of asset, you constantly have to deal with this problem of margining, liquidations, and so on. And so we feel like there's a safer way to do leverage, and that's get rid of liquidations altogether, and let's have the leverage be embedded in the contract itself. So power tokens are structurally an LP share. They are a claim to 2 tokens at any time. So if you are fed up with the earnings that you're getting from these power tokens, you can have exact claim to the underlying assets, which is really fantastic. They're not a synthetic creation, as you will. And there are 0 oracle dependencies. Because we're essentially depending on arbitragers to set these prices, you can get this quadratic payoff, as you will, on any tokens. So now not only are you getting E squared, which is formerly known as squeezed, you can get pickle squared, or really any sort of token, as you will. And this is really I think a 0 to 100 improvement on on-chain markets. So one thing that's really interesting that we've been trying to create this bridge between traditional finance and on-chain finance. So in traditional finance, one of the probably more cost-effective ways to trade volatility is through something called a variance swap. And if you look very closely to the payoff of a variance swap, you also have this convexity, right? Where as these large swings in volatility occur, you're essentially earning more. So you have higher upside and relatively limited downside. And if you look really, really closely, this is almost exactly the payoff of something like a power perpetual. So what we've, in essence, created is this type of arithmetic variance swap directly on-chain. Now, not just a variance swap on ETH, but a variance swap on any asset. And I think the potential for this is really fantastic because, LP shares on Uniswap, which are incredibly liquid, have this sort of exotic option profile. And the #1 way to hedge this, and the literature is very clear, is to use something like a weighted variance swap. And people think this is not really possible because there's not a lot of liquidity, as they're normally traded over the counter. But now, using the innovations of automated market makers, you can build a ton of liquidity behind these on-chain variance swap instruments. So to kind of predate this and put it in a greater context, ERC-20s became really, really popular because they offered this way of trading assets directly on-chain, and Uniswap came in and said, okay, we're going to build a protocol and a trading venue for trading these tokens. Then NFTs came along. You can say what you will about NFTs. I certainly have my own opinions, but they allowed you to effectively trade JPEGs on the blockchain, and then OpenSea came in and decided to build a really great user experience and trading venue around this. We see the next innovation for derivatives in these LP shares. LP shares, categorically speaking, and definitively speaking, will be the next step for derivatives. They're probably the most capital efficient and probably the most flexible way to build derivatives directly on a blockchain using the innovations of automated market makers. And so Kyle and I have a strong opinion on the innovations of LP shares, and we hope that Numoen can be sort of that user-friendly application for trading these derivatives on the blockchain. All right. Well, also last question or last point I'll make is, you're probably asking, wow, Robert, this sounds really fantastic. How do I actually try out the system? Well, Kyle over here just shipped a new improvement to the user interface. So it is available currently on numoen.com if you are interested in checking it out. All right. Thanks.
Apologies, ladies and gentlemen. Who has a question? Who has a question? Any questions here? Okay, right over here.
Is this just limited to like LP shares of CFMMs, or like can you do it on like staked tokens?
Yeah, that's a good question. So you're asking, can I get the payoff exposure on not just the spot asset, but these like interest-bearing assets as well?
Yeah.
Yeah, absolutely.
Okay.
Yeah, absolutely. That's a good idea too, to have some sort of leverage exposure on staking ETH or so on.
Hello, I'm Remy from Vest. Thank you for your speech. Yeah, I mean, speaking of the replicating market makers, I believe like the whole underlying thesis of the replicating market makers is that like, you can replicate any kind of payoffs and kind of convert that into a constant function market maker. Is there a specific reason why you chose the par perpetual like to start with as a product? I think there could be like other payoffs that would more fit with the demand, or like have a more better product market fit.
Yeah, that's a good question, and would love to hear your thoughts on which ones have better product market fit. But I think two things. One is I think the key missing piece in the derivative space right now is this convexity, right? You have convexity in traditional finance, and these convex products are far and wide more demanded than linear products in the derivative space. And then I think the second point too is out of all of the exotic derivatives in crypto, the one and the biggest demanded product is a variance swap. People want to be able to hedge their volatility on a blockchain. And so we thought, power perpetuals are effectively these variance swaps on chain. Let's try to tokenize that and bring that to as many users as possible. But good question.
JP?
Thank you for the super interesting talk. I read this paper, the replicating market makers paper, ages ago, so it's not super fresh in my mind. Yeah. But I remember that there was there was this issue with the convexity that you could only replicate a few, well, not a few, but you could only replicate some payoff functions. So could I short call or buy a put option in this?
Yeah, so
because they have the opposite convexity.
Yeah, so in theory, you always have to be over leveraged, right? So you have to have some sort of leverage LP share. So really, the system only works when you have this kind of quadratic payoff initially. But I think there are like ways. It really depends on how you're lending and borrowing the LP shares. So I think Gamma Swap has this way of getting leverage exposure on these LP shares. But as long as you have leverage in the system and the LP shares over collateralized, then you're good to go.
Okay, cool. Can I ask you a second question?
Yeah, of course.
Are you familiar with the Panoptic protocol?
I am slightly familiar with it.
Okay. Would you be able to comment more or less how it compares? Because it seems quite similar. I think they're sufficiently different, but I think they share some similarities, but maybe you can guide me in understanding them.
Yeah, absolutely. So I can't really speak to the overall design of Panoptics, as I'm just not too familiar with it. But the essential idea is Uniswap v3 is sort of an aggregate of different constant function market makers, right? It's a super flexible design. And the principal idea is you can hedge directly your LP share exposure using Panoptic. It's this two-sided AMM, and that's really fantastic. I think the big difference is we see that the majority of folks that want to provide liquidity to these constant function market makers are frankly not sophisticated enough to do that on something like Uniswap v3. You really need to be professional to market make because it's a very complicated problem. So the idea is you want to kind of split these up so that you can passively provide liquidity to these variance swap derivatives, which are otherwise very complicated, and then allow on the other side of that a buyer to get this payoff. So I think Panoptic tries to sort of scale liquidity more for something like Uniswap v3, which is designed for swaps and spot trading, whereas we're actually trying to more specifically build out these individual derivatives that other people can trade.
Thank you so much.
Hope that answers it.
Yeah, it absolutely does. Thank you so much.
Yeah. course.
Any other questions? I think we had one hand up. All right. Thank you very much, Robert.
Yeah.
All right, ladies and gentlemen. So for the rest of the agenda here for CryptoEcon Day Denver, we're going to be taking a break. Lunch is going to be starting at 3:45 Mountain Time. So everyone get ready. We're going to be having lunch in the room over to the left. And then we're going to start at 5 o'clock with Vic Kalgatki talking about island economies and how Filecoin, Ethereum, Bitcoin have their own island economies and how they will work together. But just so you all know, 3:45 is our late lunch. 3:45 is our late lunch. So please dine with us, network, and we will see you back at 5 o'clock. For everyone watching at home, we're going to get ready with our second half presentations in the next 5 minutes. In the next 5 minutes, we will start the second half of our CryptoEconDay ETH Denver presentations. Ladies and gentlemen, welcome back to Crypto Econ Day at ETH Denver. My name is Mike McCoy. I'm your MC Coy for the rest of the evening. Coming up next, we have a presentation on island economies, specifically the island life, by our very own Vic Kalgatki. Vic is a research scientist here at the CryptoEcon Lab. He is really our governance expert, our governance guru, and he's one of the few members that has been able to influence so much in the Filecoin protocol governance improvement proposals, and also be able to tell what these economies do, not only from a high level, but a very deep and intimate level of why data economies, open source economies are very beneficial in the cryptocurrency world. So with that, we're going to bring on Vic Kalgatki.
Do I just hold it, or do you want it in the stand? This is fine. Yeah. Or can I just pick it up too?
Absolutely. Slide it right out. Just pull.
Okay. We'll do this for now and then leave it. Yeah. Okay. Cool. Thanks. All right. Can everyone hear me? All right. Thank you, Mike, for another very kind introduction. So last Crypto Econ Day, I talked a little bit about cryptoeconomic governance, not just specific to the Filecoin network, but in these like decentralized open protocols writ large. And that kind of got me thinking, because like it kind of got me thinking as to where are these governance decisions being made? Like, why do we care about rules for protocols, and upon what spaces are these rules for protocols kind of being enacted? And then it kind of made me think a little bit about like, how do we characterize these blockchain protocols, each with their own different set of rules, and particularly economic constructions, and why are they all kind of like different, and what are the goals that each of these protocols are trying to achieve? So I had a conversation with a friend of mine maybe a year ago about like what is crypto, what are we doing here, what is Web3, and the kind of conclusion is, I don't know if people have seen the show Stranger Things, but there is this concept in the show called the upside down, which is this world that is kind of adjacent and parallel to one that we kind of live in, and it's very similar, but there's like this kind of little twist. And I think me and my friend kind of concluded that the world of Web3 and the world of cryptocurrencies is kind of like the world that we live in, that we kind of know, the one that is situated in like the Web2 context, but there's always this little kind of twist that's added. So the preamble, the preamble that I just gave is where I think we can get to this new another analogy or framework to understand blockchain networks, particularly layer ones, but I think blockchain networks writ large as this kind of island economy construction or framing, rather than I guess the more traditional ones that may kind of exist. What I'm really trying to say is there's maybe some tendency to situate our understanding of protocol revenue, of kind of the transferring of value in ways that are fairly similar to ones that we already know. Like think about like a balance sheet or an income statement for companies. A lot of people kind of try to apply that same logic to blockchain networks. And in some ways I understand why one might do that, and that's because that world is fairly new, that world is fairly well understood. But then it kind of brings me to this upside down concept where maybe that analogy doesn't really work, which is why I think I want to kind of talk a little bit about island economies, what they are, and why blockchain networks can kind of, you can draw more and like better parallels by understanding blockchains as these like kind of mini nation states with their unique use cases and differentiated goods and services. So I just want to give like a brief kind of overview of a loose definition of what island economies are. This isn't necessarily formal, but it's more just like a mental model or framework that we can use as we apply this to digital spaces or to blockchains. So at a high level, an island economy is just this isolated area it can be physical, like Singapore, or virtual, in which like individuals and actors can survive, thrive, and they can do so without having to do all the work necessary for self-sustenance themselves. Said differently, there's a division and specialization of labor. And you can like this economy can be characterized by some degree of self-sufficiency, but not complete self-sufficiency. What I mean by this is there's some lack of resources that need to be brought in from external economies, or there's some dependence on external economies, and participants can kind of freely move in between in between these different spaces. So a participant that is a member of the island economy today doesn't necessarily have to be one tomorrow. Similarly, a participant or individual who is not part of the island economy today can be, part of the economy in the future. So then the next step is, okay, so island economies are kind of these isolated spaces. We can think of blockchains as these digital island spaces, right, where there is some kind of transference and holding of value, usually represented by some kind of token, and that transference of values kind of specific to like the space that those goods and services within a particular digital asset space contains, but it can touch other ones. So blockchain networks writ large offer some combination of goods and services. If not, people will not use them, right? Because we value the kind of productized offerings that different blockchains kind of allow. That transference of value and the production of that value is kind of facilitated by some kind of token. The token usually represents value, but it also facilitates the transactions of different, kind of goods and services that are valued as well. And then as a result, these kind of different blockchains all have these differentiated and specialized goods and services offerings. What I mean by this is we can think maybe to the kind of decentralization trilemma of there are all these inherent trade-offs between scalability, security, performance, etc. And as a result of these kind of implicit trade-offs, blockchains can and will specialize in different areas of this. And as a result, the crypto-economic kind of incentives and constructions that underlie that transference of value can be very specific to the goals of the token economy itself. It might not make sense for like a blockchain like Bitcoin or Ethereum or Filecoin to have identical crypto-economic constructions, and that makes sense because they all offer kind of different productized offerings. So I think the most basic example is always kind of like Bitcoin, right? Like that is the kind of primitive that underlies a lot of the work that is now that will be done in the digital kind of digital currency, but the blockchain space. And the question that you can kind of ask is like, what good or service does Bitcoin as a blockchain or as an island economy kind of produce? And the short answer is, and feel free to disagree if we want to talk about this more, but the short answer is that it might export like this globally accessible, trustless, permissionless transaction ledger, as well as like the broader ethos of Web3. So that has some inherent value that is represented by the token, which helps facilitate those transactions. The security and what is kind of, I guess, valued by some part of that value is due to miners bringing in resources from the external world, right? Like ASICs aren't a part of the Bitcoin economy until they're plugged in and then start mining Bitcoin, and then they're contributing to consensus security. But where did they come from? They came from external economies, from the physical world, and that is the kind of bridge that allows an island economy such as Bitcoin to kind of grow, amass resources, and become fairly like a large critical part of the Web3 ecosystem today. I have the slide here, but now you can all see it. I just talked over it, but now the graphic is there if that changes anything for you guys. So yeah, and then you have these base primitives. They kind of grow. The Ethereum island network, I think, is an interesting one, right? Because you can think of Ethereum as like this kind of mother island, this base island, and you have all these like dApps, etc., scaling solutions that are kind of dispersed around it, but they're all anchored by that base kind of island economy and the almost world computer services that you have with the Ethereum blockchain. So I think a really good case study is probably that I'm going to dive into deeper is a Filecoin island economy. And the reason that it might be easier is because I primarily spend most of my time working on Filecoin, but also because I think it's a fairly interesting and I think complex yet simple system if you were to, depending on how granular or high level you want to get. So I think everything in blue kind of represents what is happening in the island economy writ large, and the part in black is a part I kind of talked about earlier, which is the potential for inflows and new clients, new kind of applications of what Filecoin offers to kind of enter the economy. So the Filecoin island economy can be characterized as like these interactions between different stakeholders. Loosely, you can define them as storage providers, researchers, developers, token holders, and clients that kind of consist of the economy. And the raw resources that kind of contribute to Filecoin are, at the moment, the amount of storage capacity and hardware that is committed to the network is underlying not just consensus security, but the kind of value that is being brought in from the external economy, right? So in island economies, Filecoin didn't just start with 14 or 15 exabytes of storage capacity. It is brought on and onboarded by individuals committing resources to the network and incentivizing, kind of more capital and goods and services that kind of enter the economy. And then as that grows, you have you have a critical mass of raw resources, and then you have people like researchers and developers kind of creating these nice packages of storage-related goods and services that take these raw resources, harness them, and use them in different ways that may be demanded by different clients or users. And that's the next part of value generation. It's not just the amassing of raw resources in an island economy, it's the productization of those goods and services. The productization of those raw resources. It's not merely sufficient to have a bunch of hardware just kind of plugged in. The next step is to take that hardware and use it for something like archival persistent storage, or for decentralized content delivery, or for compute over data, et cetera. And that is kind of the next step to value generation, which is taking things that are committed to the network and then kind of using them in productive ways. So there are a multitude of ways that island economies can benefit. Can grow. Either an island economy can grow just from more commitment of resources, or it can go from the productization of those committed resources, which I think is kind of due to the interrelated actions of all participants. You need storage providers and to commit those resources, and then you need all the other kind of ecosystem and developers to build to take that and kind of use that in a productive manner. So I think the final thought is, the island life is a good life, I guess is the title of my last slide. But I think the key points to really hone in on are, there are a lot of frameworks to understand protocols, blockchains, what's happening in Web3 writ large. Like, a lot of people think of valuations and valuing things in a certain way. I think we can take a step back and instead of trying to situate things in the context of like the Web 2 and frameworks that we already understand, like a balance sheet or an income statement, et cetera, or some kind of profit and loss construction, I think we can maybe think of blockchains as more organic spaces that have the ability to grow and kind of garner resources similar to a way that like a nation state would in terms of trade and specialization of the goods and services that they can offer. Given that, though, there's some dependence on external economies, not just within Web3, but there's dependence on individuals to amass resources from the world writ large. There's always some kind of physical component that is that underlies the packaging of resources and goods and services, and as a result, like a good island economy with healthy cryptoeconomics benefit from a situation in which stakeholders themselves are kind of incentivized and aligned to generate value because that also that kind of grows and brings in external participants and resources, accruing value, kind of perpetually accruing value back to users and individuals building, creating that value. So those are kind of my final concluding thoughts. I hope that's kind of a useful framework to think about blockchains, and maybe to think about how like we think about the utility and value of these different chains and offerings going forward. So thank you, appreciate it.
Thank you. Thank you for the presentation. When you were describing kind of the island economy and how the island can benefit from specialized services, is it that something? And I'm not sure if you're familiar with like a kind of free market like by Adam Smith. Basically, what he was saying is like every country should be focusing on what they are doing the best. So an example can be like France should be producing wine because they know how to produce wine. Germany should be producing beer. They should basically then just like trade between themselves like, okay, you have better wine, I will buy wine from you, and you have better beer, I will buy beer from you, rather than like both trying to do the both products. Like, is that something like how you think about the blockchains? Like, there should be like fairly specialized and like whatever they need, like other than that, like they should kind of like trade in, trade out?
Yeah, so like what you're kind of really talking about is relative opportunity cost and gains from trade. So that is like a pretty kind of base level like macroeconomic concept that I think is a good characterization of kind of what I was alluding to. I wouldn't say that like there's only one thing that an individual blockchain can do, but there's always some degree of specialization that benefits participants across island economies, because you're right, there is not just like, there aren't siloed, there are bridges between, let's say, Ethereum and Filecoin, in which like Filecoin can be maybe considered data availability layer, and then Ethereum is like kind of the computation and kind of application layer, and that each consensus mechanism, each blockchain kind of benefits from their relative strength. So that's a fair, I agree, I think. I don't know if there was a question there, but I don't necessarily disagree.
Hey, thanks for the talk. So to go with the analogy, what do you think would be like the most valuable trade partnerships for Filecoin to have? And maybe underlying that question is, how do you think about the value of Phil token and how that benefits from trade?
Yeah, it's an interesting question. I think it's less a question of what may be the most beneficial like partnerships per se, and more about like what is a specialized offering that you can garner from a decentralized storage network and all the things that you can build on top of that. The short answer is I think most projects or most parts of most ecosystems benefit from some kind of infrastructure stack. If this is like the most robust one that offers the services that they're looking for, then in general I think there's always gains being had from other like kind of projects leveraging that infrastructure stack. Does that answer your question? Okay.
Hey, thanks for the talk. I was wondering, getting back to your island analogies, have you explored to what sense are the islands playing with each other, zero-sum games, and to what sense are they playing non-zero-sum games? And maybe try to have you tried to do some kind of a modeling? And I'm wondering because like you can see a lot of projects are basically, it seems that a lot of the games are zero-sum, at least like the meme games, like we are the most decentralized, we are the best in this. Yeah, just your general thoughts.
Sure,
have you ever explored?
That's a good question. Thank you. I think the part that doesn't make it zero-sum is the black part there, right? So the idea is like, the reason why these games aren't zero-sum is because there's always kind of this incentive to bring in extra value from external economies. If the value was kind of generated solely internally and was circulating internally, then there is a kind of finite amount of resource and value available. But if kind of the goal and incentive alignment of participants is to bring in value, like for example, to bring in ASICs to Bitcoin, there is always that incentive because if you contribute more hash power, you receive a larger share of block rewards. Filecoin is to some extent similar. You commit more storage capacity or onboard more data, then you also receive a larger share of the block reward, right? So that's kind of what doesn't necessarily make it zero sum in that way, because where do those resources come from? They come from the external world, so that value is being kind of transferred and injected into the island economy itself.
My point is you can see both, right? You can see a really complementary use cases and non-zero-sum games. You could also argue that you have zero-sum games as well, like if you are claiming, for example, Filecoin, we are the best solution for storing your files in a decentralized way. You have Arweave, you have different solutions, right? And so to some sense, they are also playing zero-sum games with each other for the external users, right? If a third
okay. I don't see that differently than like competitive product offerings operating in the same total addressable market, though, right? Like what you're really saying is that there's some competition for some consumption of goods and services. That's probably a good thing because that incentivizes the product offerings to be better.
Yeah, of course. My question was more like, have you guys tried to model it and play out like what would be the end state? Like, would it be more multi-chain, or would it be more like power law distribution that in any kind of area, let's say data, there would be one player that would have like 80–95% of the market, and then there would be a long tail.
I see what you're saying. I don't think modeling explicitly with like regards to kind of looking at the distribution or how many protocols or whatever would exist for certain use cases is something that we've really looked into. You can look at different like conservation regimes within a specific economy, but like that part that you just asked about is, I think, a different question than the one that we're thinking about here.
You can tell we came together because we have related questions. Are you familiar with regression theorem?
Regression theorem? I'm not sure what you mean by that.
Okay, if not, then that's fine. So let me ask, how do you see a transition of any of these coins, crypto in general, from like a commodity in its own respective chains to generally accepted medium of exchange? Have you thought about that, like how that should play out?
Sorry, can you answer? Can you just restate the question? I don't think I follow that.
So, all right. So, just in like one sentence, what regression theorem explains is how does a commodity become money?
How does a commodity become money?
Yeah.
Okay.
How did gold become money? Basically, that's the main story. And my question is whether you see this this path compatible with any of the chains where, like, you know, in ETH or Ethereum, ETH is used for gas. It's the main commodity. And do you see that path being valid? And you know, how if yes, then how do you feel that playing out in this island economy analogy?
Yeah, I mean, I think to some extent, Filecoin is there's a similarity given that Filecoin also produces and exports block space. There's also gas that is demanded because storage providers are also mining to compete for blocks as well. So I don't really see it that differently than something like an Ethereum, at least at the gas level. There are definitely some nuances given that I think we had some talks earlier today from other researchers within CryptoEcon Lab, but I don't know. Apologies, I'm not really answering your question. But if the question is like, do I see like gas as a commodity that kind of generates value? Sure, because it's a resource that is demanded and also produced and exported by the chain.
All right, we have time for 2 more questions, here and then there.
Hi. So my question is somewhat related to the first one, but I'm curious, like, how do you see that the island economy idea kind of like represents every player in this space? So for instance, like Ethereum, would you say that it also will gravitate towards becoming an island? Because it seems that their motivation is more like becoming like the one place where all programmable smart contracts can live in. So it seems that they aspire to be more of like a continent rather than an island. Do you think that's a good motivation on their end, or is a better world where every value add is its own chain with its own set of validators? What do you think about that?
Well, a continent is just a really big island, no? But I think, in terms of what the goals for like Ethereum might be or might not be, I'm not really sure I can speak to, but I still think what you just described, the framework kind of holds, right? Like, how does that happen? That happens from lots of value being generated within the economy from developers and researchers, a lot of resources kind of being committed, and then that value generation happening because you're kind of productizing those goods and services really well. I think that this is less like a kind of statement or judgment on like size or kind of like what something looks like, and more just a framework to understand how these blockchain economies can be thought of.
I kind of have a TradFi question of how do you value an island economy? Or have you thought about ways to sort of put some numbers or parameters around how one might think about it?
Yeah, that's a good question. It kind of gets back to the upside down like analogy, right? Which is like we have some understanding of the utility or the production of a country, and like we have some metric like GDP, right, which kind of constitutes the value being produced, let's say in a given year from a country or a nation state. Is there some kind of analogy to Web3? Potentially, right? Like because an economy exports like Ethereum exports our block space, Filecoin exports block space as well as like storage capabilities. There's some value that you can attach to that. It also kind of brings in and imports things from the external world too. So I'm not going to say the comparison is one-to-one, but there's like, I think the reason I kind of brought up the island economy is because I think it's more, at least, honest or faithful to like what value is being generated from like in blockchain to at a high level.
Thank you very much.
Cool, thanks, appreciate it.
Ladies and gentlemen, always good to get an inside look into the island life. Next up, we're going to bring up Alex Stokes. Alex is a researcher at the Ethereum Foundation, where he focuses on the effects of MEV, maximal extractable value, on open blockchains like Ethereum, and mitigating externalities in the long term. And other than that, he's a very deep and he just has a wicked mustache, and he's going to really blow your minds with all his knowledge. So with that, Alex Stokes.
Thanks. You can keep it on here, but can everyone hear me? Hello, hello? I'm going to raise it up a little bit. I'm tall. Yeah. This is good, yeah. Okay, hello. I can hear myself. That means you can probably hear me. And there's a little clicker. Great. Okay. Hey, everyone. So, yeah, we're here to think about MEV and Ethereum. Yeah, I'm Alex Stokes. I got a nice intro there. Researcher at the EF. If you want to find me on any platform, there's my handle, rlxstokes. Feel free to reach out with any questions or anything like that. So, the first question, like, what is MEV? You've probably heard about it a lot. Many of you, if you're in crypto, you've certainly heard about this thing. And Yeah, it's actually, I think, a pretty big question. It's like something that's like very much nerd sniped to me. I put here, it's this question that only gets more interesting the longer you sit with it, which I think is very much true. MEV is like this initialism for like minor extractable value. Well, we pretty much got rid of minors, so now there's maximal extractable value, or just MEV, and it means this thing that we all know what it means, and it doesn't really matter what it stands for. Yeah, so at the end of the day, what exactly are we referring to? Well, when a block producer goes to make a block on one of these networks, like Ethereum, Bitcoin, Filecoin, any of these, pretty much all these protocols give this block producer this like degree of freedom to order the contents of the block however they choose. So that could be like including no transactions. It could be including like just the miner's transaction, or like a whole spew of transactions. And usually there's like a public mempool. So if you like go to use these protocols, your transaction ends up in this public mempool, and from there, most implementations try to be like fair in some sense with respect to like the market mechanics that they have. So that could be like, I take like the top in highest paying transactions in the next block relative to its size. And now that we have this like list of transactions, it turns out that like the situation gets like very, very complex because it turns out that by having this like set of transactions, you can reorder them, you could take them out, you could put others in, and this turns out to actually have value to the person doing this. And this is what we mean when we say MEV is like this value that can happen from this game playing with the transactions. So I'll give you an example just to make this a little more concrete. This is the sandwich. You probably heard of like sandwich attacks. And what we're going to do is we're going to like use Uniswap on Ethereum. We're going to look at the USDC ETH liquidity pool like at this moment in time. This is an important point. It's like a snapshot. And we see the prices at 1656, USDC for 1 ETH. So I'm going to say, hey, I want to buy 1 ETH for this much USDC. And moreover, well, I'll explain why in a second, but there's this thing called a slippage that we also have to set along with our sort of intent to trade. And we'll say the slippage is like 50 bips, this 0.5%. What this means is that basically my order will go through the Uniswap exchange, not just at the price that I claim, the 1656, but like with this like buffer, right? And so this is the slippage. So I could basically take, basically a 50 or 0.5% extra worse price to let my trade go through. And the reason we do this is because what can happen is I look at the pool, there's a snapshot in time, I have to like get my transaction on chain, and there's like some delay in there, right? And things could happen, like there could be some huge like market volatility, other things, there's also like liquidity effects. Point being is you could end up with a situation where if I don't have some like wiggle room, so to speak, then like by the time my trade goes to settle on chain, it'll just like be invalid because the price will have moved away from that. So we have this thing here, and that'll be important in a second. Yeah, and so basically if we can somehow say, okay, at this point in time, let's say just after this last block, we're like the very first transaction in the next block, and at the end of the prior block then, this was the Uniswap price, and that's what we could trade at, and we're happy. The problem is when that's not the case, and usually it's very hard for us to say, okay, stop the whole blockchain because it's decentralized, right? Stop the whole blockchain. I'm going to look at the price or the state at the end of the block and then become the very first transaction in the next block. So this is now going to open up ourselves to the sandwich attack where someone's going to take advantage of the slippage that I was just describing. So the first thing they'll do is a front run where basically they'll look at the price of the pool. They'll insert a transaction before mine that drives the price high enough in the pool such that my transaction will still go through, but it'll be like the worst price that my trade could execute at. Basically like the max slippage that I set. Then my trade will go through because that's what I said I was okay with. And then yeah, what happens is because of this, the attacker who bought these tokens before me can then turn around and sell them. This is the back run. And together, this is the sandwich, right? You have like a trade on either end and the stuff in the middle, your trade. And yeah, basically what happens is there's some amount of tokens I would have gotten that I basically lose to the attacker. That's why they call it a sandwich attack. And yeah, that's probably not something I'm that happy with. So this is an example of MEV because like, if I didn't have these transactions in this sequence, then like none of this would have happened. I would have just had like whatever arbitrary execution of my trade, and it would have been fine. But this is what we mean when we say that it's up to the ability, or like it's a consequence of the ability to be able to like manipulate the transaction sequence that leads to this type of this whole idea. And as we'll kind of see, like this slippage thing was like important to the Uniswap protocol. Like it was necessary for the DEX to be usable because otherwise the liquidity pool would just move before you could actually get your trade on chain, and so basically everything would revert, right? You'd get very few of your trades actually going through. And so that's why this parameter exists in the first place, but in the same breath it opens you up to this whole can of worms of MEV. And yeah, like why do we care? Every mechanism discussed today throughout like the whole day of talks, they basically all expose MEV. This is a thing that is just like a very general concept, and like sort of the more you look, the more places it arises. And so then the question becomes like, what do we do about it? Like, if I was like, hey, I have this new DEX, but like you're gonna like lose money by using it, like necessarily, you're gonna tell me, well, I'm not gonna use that. Like, of course not. So now it becomes this thing to think about for people who design these protocols and also use them. Have some like MEV-aware concepts in like your protocol design. MEV again is this like sort of like raw incentive you can use to like do powerful things. You can like use it to directly drive like behaviors of people doing these or using these protocols. But yeah, like we saw with the sandwich attack, like it really opens you up for some unintended consequences if you're not careful or thoughtful about it. So that was like what is MEV in a very compressed amount of time. So now we'll talk about it on Ethereum a little more specifically. And a helpful way to think about this, there's this diagram made by the Ghost app. He was at Flashbots. Some of you might know him. Either way, he has this idea of the transaction supply chain, which I think is really helpful. And what will be really cool, I thought there's like a laser pointer. There's not. Anyway, so point being, cool diagram. This is like a really helpful mental model for thinking about this stuff. So, on the very left-hand side, we have like the user. Presumably, we've all used these blockchains, or we can imagine using them, so we kind of know what that's like. The user then, talks to their wallet and says, "Hey, I want to like make some token swap," for example. The wallets then like somehow get those transactions, more closer to the protocol. And in the MEV context, what that looks like is, at least with the situation partially today, is your wallet would take your transaction, it would be gossiped to like the public mempool where anyone could see it. That's where these entities called searchers would then see these transactions and try to like extract a MEV from them. The example of the sandwich attack, the attacker here is like the searcher. And so you have this transaction flowing through. Searchers then work with builders. Builders here referring to building a whole block. And we'll see why that's important in a second, but basically an entity who's going to make a complete block. The reason you differentiate between builders and searchers is because searchers are like very specialized. There's usually like a team of searchers who like do just liquidations or like just ARB or something like that. As opposed to like this whole bigger task of like making a complete block. Then what the point I'm building to is where then you have builders being able to pass these like complete blocks they've constructed onto validators. And yeah, this is just like a useful model for like thinking about all the different actors in the system. So MEV exists. It's definitely on Ethereum. It's everywhere. And it's bad. It's bad in like the very like sort of like acute cases where it's like, yeah, like I got worse execution than I would otherwise on my trade. But it's also bad in like a much bigger sense because it does all sorts of things to like destabilize consensus and like the security of your chain. So like for example, if there was like a huge liquidation, well this liquidation exposes MEV because if I can like back run the Oracle update, then like I can like collect all of that, the liquidation fee. And so what that does is if you have something like this, then now there's essentially this like huge bounty to like reorg that block. Because then anyone else, the next proposer could go and try to like capture that and like reorg that block out of the chain, capture the fee for themselves, rinse and repeat. If you do this like forever, then like the chain just halts, right? Like it doesn't go anywhere. So that's actually very concerning. And Moreover, yeah, so yeah, it turns out MEV is like quite bad. So that's one thing, is just like destabilizing consensus, and like I think what originally brought me into like looking at this. But separately, it's concerning for like a more subtle reason, because even if you don't do anything bad or like quote that would attack the chain, it still is this like very centralizing force. And the reason why is because let's say I have like 2 validators and one of them is better at extracting MEV. Well, of course, now they like offer some staking service. So then if they go to advertise that to you, then like me as just like random rational consumer, I'm going to like go to the one with higher returns because they're the one that's better at extracting MEV. Now, as they accumulate more stake in this way, they have like more resources to like get better, and it's this like flywheel where in the end you end up with like basically everyone delegating to like the one, bank that's extracting all this stuff. This is not good. In Ethereum, we want like a very broad, diverse, decentralized validator set, and so this like core mechanic of like collapsing everything via MEV is not very good. So like, what can we do? And the like immediate answer is we go back to this diagram here, and we just say, okay, well, if there's this like huge MEV thing that's like trying to like collapse all the validators into like one sort of like, entity here at the end, we can just try to like somehow firewall the rest of this like MEV stuff such that it doesn't affect the validators. And that's what I try to draw here, just basically like a firewall. This idea is proposer-builder separation, the proposers being the validators. It has this acronym PBS. If you follow this stuff, you've probably heard this at this point. And yeah, it's essentially doing what I just said. We want to somehow like, even if like, the MEV doesn't like, these MEV problems don't go away just because we do this, right? There's still all this stuff happening sort of outside the protocol, but we can at least keep the validator set of the protocol. We can keep these pressures off of them compared to like the status quo. So that being said, there's a very big design space for how to do this. And we definitely want to be thoughtful about how we like roll out PBS before we like enshrine any particular thing. And so obviously the question is like, what can we do in the meantime? Well, we can do PBS off-chain. And this is MEV-Boost that I will go into a bit more later in the talk. Yeah, the rest of the talk I think I'll like kind of narrow in on the PBS stuff, but just to call it out, like there's a lot happening everywhere else in this pipeline. Like there's a ton of R&D, a lot of like very interesting work happening. So really, basically, we want to like recognize this as a problem at like every point in the stack and think about how we can improve it somehow, right? So for example, if you have these like set of builders, it's like, can we think about decentralized block building such that like it's a party of block builders and not just like the one centralized entity that's like, controlling the whole thing. They become like the gateway onto the chain. There's innovations at like the wallet level. A big thing coming up is like MEV rebates. So basically, we take our sandwich attack and we say, okay, rather than like having someone background me and taking the profit for themselves, what if instead these like searchers, they would like, basically bid me or refund me most of the background. And the cool thing here is it actually could go to like subsidize like my gas fee. So you can imagine I basically let myself be sandwiched, but then I trade for free, which is pretty cool. And there's like a whole design space here that again, I think we'll see a lot of cool stuff come out in the next couple of years. This isn't just a protocol level concern, also applications themselves. There's like minimize MEV in the first place. Generally a good thing if it's like quote toxic MEV. If it seems like it harms your users somehow, you should like definitely think about how to minimize it. There's also utilization. I tried to allude to this a second ago of like MEV is actually this like design primitive and you can use it in like possibly really creative ways. One way to think about it is just as like a bribe. So it's like, oh, my protocol does something. I mean, like, all these protocols with liquidations, like they kind of follow this pattern where it's like anyone can go and initiate the liquidation, but someone needs to do it. And why do they do it? Well, you're going to pay them some finder's fee. This is an example of that. You've probably heard about Flashbot's Suave, which again is like attempting to like address this like issue of builder centralization and like higher places up in the stack here. There's a bunch of applications, Rook, CowSwap are some that are like more targeted, explorations of these different ideas. And again, there's like a huge long tail. Yeah, I just want to call those out. So PBS, proposer-builder separation. Today we have this thing called MEV-Boost that does this off-chain. We would one day eventually like to enshrine it in the protocol. The question is, how do we do that? And yeah, so we'll look at PBS now. 1 second, I'll take some water. Okay, so there's this thing called MevBoost. Again, it's been a bit of a hot topic recently for reasons you'll see in a few slides. So if you follow Ethereum at all, you've probably heard about this. What is it? It's this off-chain implementation of PBS, so basically trying to like host this market for proposers to work with builders in a like decentralized, trust minimized way, and have it done without any protocol support. The implementation, the research and development has been stewarded by Flashbots in collaboration with a bunch of Ethereum researchers and developers from teams all over the space. Really cool to see. And yeah, if you want to like dig in, there's a link here to learn more. So how are we going to do this PBS thing off chain? Well, this is the core problem, right? You have proposers, they want to sell block space maybe. You have builders who want to buy block space, and builders want to buy block space because they are working with searchers, or they are a searcher, or however it's constructed. They basically have a way to say, hey, rather than the proposer just like have some some use of Ethereum block space, they could take the same block space and use it more productively for their version of productive, right? And that's what we mean by them being this actor who can like extract some MEV, and then now there's like extra value that is within each block. That's what I tried to show here with this like gold outline. So it's like you have blocks in the chain. So this is specific to Ethereum, but basically the idea is there's a consensus block, an execution block. You can ignore that. I borrowed these from a different talk. Either way, illustration is you can imagine transactions being in green here, and there's like some MEV they carry, right? And that can vary over time. It varies from block to block. And so you have that. And so then the question is like, okay, if I go to propose the next block in the chain, what am I going to put in there? Well, as a proposer, I could like try to be naive and just like grab some stuff from the mempool and like call it a day. Or I could work with the builder who might be a little more sophisticated about the type of payload they construct, and this is what PBS sets out to do. So yeah, here's just some more diagrams because pictures are fun. We have block builders, we have proposers. The question is like, how do we connect them in a way that's decentralized, also trust minimized, and yeah, relieves this pressure. Because the whole point here is that we want to make it so that proposers can be naive. Like I use that word, and it's really the point here is that we want to make it such that proposers can still like have some like benefit from this MEV thing without needing to like themselves specialize in that, because that's how you lead to these like centralization pressures where it's now very important for you to like almost have this arms race to like be the best MEV extractor, which then basically means, well, I'm just going to give all my stake to like the banks. This slide's not important. And yeah, so I'll just continue like with my diagrammatic explanation here. So the way we're going to do this, right, so what we wanted was we wanted some way to connect builders to proposers. We're going to do this thing. It's just called MevBoost and declare it exists. And it's basically a way to connect these two networks. So let's kind of think about how that would work. So one way is you basically now have an auction where builders, for each slot that they want to like submit a block, if they built a block for like this slot in the protocol, then basically there's a way now via MevBoost for proposers to query for these bids. A rational validator, a rational proposer will obviously pick the highest one. So you can see here they picked the block. There's like maybe 3 bids. One of them had like a lot of this MEV or just a high bid in terms of value to pay to the proposer. That's the one they pick. That's the one they include and get on chain. Yeah, so there's a problem here because it's not as simple as like, oh, I could just like have builders just send these payloads in clear text and have that sent to proposers, and we call it a day. And the reason why is because Ethereum, again, has a very decentralized validator set, and so you could even have some home staker, or like more dangerously, you could have a rogue actor who with like a fairly small amount of like stake or capital could come in and like try to abuse this network. The reason why we care about it, or like the attack here that we're building to, is that because these payloads are valuable, you could imagine a case where a proposer, someone tries to use this thing, they basically take the work of the builder, but then like strip out the parts that the builder has designed such that they're compensated for their work. This is like MEV stealing. And we don't want that to happen. And it's a problem because we want this to be like again a very decentralized system. And if that is the case, then like you can imagine I again try to like steal a bunch of MEV for like a very small amount of capital. So that's a problem. What are we going to do about it? And yeah, this is just more of an explanation of what I was saying with this MEV stealing. The idea is that a builder has built the block. They are going to like basically send a payment to the proposer, but then also keep some of that for themselves as like compensation. And a validator could just turn around and say, well, you gave me the clear text block, so I'm just going to like take out your payment bits and like still include the rest myself. So that's not fun. And how do we do this? Well, there's kind of two high-level options. The one is just say, only let trusted validators use the thing. But again, that goes against our like key constraint that like the system should be trustless. Otherwise, we just have to like remove the trust assumption. Pretty obvious trade-off. So the question is, how do we do that? And we're going to take this previous thing where basically we just like send a bunch of bits in clear text and have this like commit reveal scheme. What this means is that rather than send the payload over, the builder will send a basically commitment to it, a like cryptographically binding commitment, such that the validator can't see the payload, but they can opt in to that bid, and by doing so, they both bind themselves. Well, they bind themselves to the payload, and then that's revealed to the builder, who then can reveal the full payload. And we'll look at that in more detail. So yeah, essentially what happens is you have a proposer sign over a block in a way that commits them with respect to like slashing in the protocol, that they're going to go with this bid and no others. And this is an important catch that like because of this, builders have to like reveal the full block after they have to basically play their part of the reveal step. So again, here's a diagram. Builder sends over this blinded payload. Proposer picks that one. They basically send this full block, which again has this like slashable property behind it, back to the builder, who then sees that, and when they verify that themselves, they know that everything's good to go. There's no way for the proposer to then turn around and like change the block and like steal the MEV. And so because of that, then they can release the full payload, and that lands on chain, and everyone's happy. So there was this last step that's like annoying, which is that the builder has to release the payload. They have to do this like very last step here. And if they don't, then basically what happens is like there's actually not a complete valid block, and so like that can't be part of the chain, and so the proposer would essentially lose out on their proposal for that slot. And this comes down to like a weakness of the model, this like availability attack, where basically a builders can grief proposers by not releasing this block, right? So that's not good. And we have another step, another actor is entering the picture to like resolve this tension. This is the relay. And basically relays, again, are these like trusted parties. Rather than have to like trust proposers or trust builders, we like sort of localize it all into this one actor, which again, it's not ideal that this is here, but it's like easier to reason about if it's like this one thing. And yeah, so relays are trusted then to do a couple things, basically paper over these frictions between proposers and builders. A big one is like custodying these payloads such that when a proposer selects the block, they make sure that it can be released and end up on chain. Relays are trusted by builders, or rather builders trust relays not to like steal their MEV, leak their MEV, these types of things. And the cool thing though is that while they are trusted, you can have many of them, right? So there could be like many that are competing in some sense, and then that might help things in the meantime, especially until we get to like a more robust solution with some in-protocol PBS. So this is a modified diagram. There's a lot going on, but it's like trying to paint the full picture here. We got to this design where there's builders, there's relays who are basically intermediating between builders and proposers. The idea is you have many builders, they could like work with any relays they want. Here I have sort of like a fully connected model where builders for every slot send all of their built blocks to every relay. You have this MapBoost software that's talking to all the relays that it's configured with, and then from there, the validator can use MapBoost to figure out, okay, give me, for example, the most profitable block, that's the one I pick. So cool, like, this design rolled out around the merge, and it's been some months since then, so like let's look at what's happened. This was actually just this morning, so I took these screenshots. So, the last 24 hours, basically every validator has used this thing, which is like pretty wild. There's this metric of Flashbot's dominance because they are like the predominant relayer here. Because the relay is this very like trusted party, then it is very important that they don't do dangerous things. And so when we see one centralized party with this like huge concentration of interest, that makes us a little nervous. So that's something to track, although for what it's worth, the number has been much higher and it's come down a bit. You see there's 10 active relays. That's actually really cool. I think there might even be 11 recently. Either way, this is like just within, I think, probably the last 24 hours, which relays have like sent a block or like a block has come through them. Point being, there's like a pretty healthy relay market as well. That's all. These are all stats from mevboost.org. There's a lot of cool stuff there if you want to check that out. Below, we have stuff from mevboost.pix. This is by Tony, who does really awesome work. Definitely go check out this website. And it has a bunch of these like really cool diagrams. On the left here, you see this is basically like payload delivery, or like out of the blocks that were built, which relay delivered them, to the chain, so to speak, which proposer used which relay for each slot. And so we see that, the relay ramps up, and then basically over time, the distribution gets a lot better. It's pretty concentrated at the beginning, but it is improving, which is good to see. Same thing with builders. There was like this very huge concentration in the beginning with like the orange stripe is like the Flashbots builder, but you see other builders entered the scene and started to gain market share. So things are trending at least in a competitive direction, which should help. A lot of these properties or these concerns around censorship resistance and things like this that the relay could definitely could pull off. So yeah, are we good? And the answer is no. That's a leading question. Pretty immediately, the downsides of this relay model and like having this trusted actor like became apparent. Again, if you follow this stuff, you've probably seen this chart or at least heard about it. Many of these relays out of this active set, they follow these like OFAC guidelines, which are a set of like United States regulations that say some things, for example, traded cash, this like privacy application on Ethereum, are sanctioned. They should not be used. And anyone using them is like facilitating sanctions evasion, which is like really bad. Can't do it, don't do it. So yeah, that's not a good situation. Point is yeah, basically because these relays have such a central place now in the protocol, or at least this thing right next to the protocol, they kind of have this power, and this power became obvious when suddenly they needed to start filtering these transactions, which then erodes this like property, there's value of censorship resistance that's like really core to Ethereum. So, is the mic still working? Okay. It sounded like it went out, sorry. Yeah, so that's not good. And this is just kind of a fact of life right now with the current mevboost model. You can see that the relay share is improving a bit, which is good. So that's kind of, okay, we talked about MEV very quickly. There's a lot more, if that's your takeaway. If there's one takeaway, it should understand there's a lot more going on here. But that's one part of the picture. With PBS, we talked about that, and PBS kind of to date and how it's been rolled out. And yeah, now we'll look a bit about what's next and where some of this is heading. So yeah, there's sort of like different horizons or trajectories to think about. There's like longer term for this idea. There's like shorter term or more midterm, and then in the very short term. In the long term, we want to get rid of relays and improve upon this situation entirely by just getting rid of the relays completely, right? And so one way to do that is basically take the things that the relays do, but put it in the protocol somehow. There's a couple designs. I think like the most cogent one so far has been from Vitalik with his like 2-slot model, where basically rather than each sort of slot of or round of the protocol be one where you make a execution block or like a user-facing block, you'd basically have one slot for like builder coordination and another slot where the proposer takes the builder's block and actually makes like a block like we think of today. And yeah, that's there's an ETH research link here if you want to learn more. That's one idea. Another one is Barnabé Monod. He has this concept of PEP-C, and basically his thinking or his question basically around this line of investigation is saying, well, so still with like even this 2-slot PBS, we're taking the mevboost model where there's an auction, like there are bids made for a certain value, I pick the highest value and that's the block I go with. So it turns out, I mean, if you think about it, right, that's like only one way to even do an auction, or like more generally just to like think about coordinating these like different parties around the protocol. So with PEP-C, the idea is what if rather than have one particular model, we make this like some generic or some programmable model, some form of programmable commitment. And it's a very interesting idea. Again, another ETH research link. Please check it out if you're interested. There's a lot of questions here is like the bottom line. Personally, I don't see an in-protocol PBS happening anytime immediately soon. Lots of R&D left to do here. So that's cool. And closer in time, near on the horizon, we can think about, okay, if we're not going to have like in-protocol PBS, soon, then we need to improve MevBoost that we have today. And again, there's like a lot of different things we can do. One really cool thing that's come out pretty recently is this idea of an optimistic relay. This was in response to the data that I'll walk through in a second, that basically we're already seeing this just from relay operators and like watching builders and how builders use the thing. We're already seeing this idea of a latency game with the MevBoost network. What I mean by latency game is that basically if we're all competing as builders to like get our block into the next slot on chain, it turns out that we basically have this arms race where like the faster we can send a block, the more likely we are to like win the auction, and that's actually not good because basically it just means you have this similar dynamic where the better builders basically win more of the blocks, and you have this flywheel that leads to these centralizing pressures. So generally, latency games are bad. We don't want them, but there is one. And you can see it here in this data. So on the left here, this is a graph from Casper Schwartz-Trilling. He's at the EF with the rig team. They do a lot of cool like applied game theory and different mechanism design work like that. So what this is showing is basically the probability distribution of a winning bid and like when it arrives relative to the slot. So on Ethereum, basically blocks come 1 block per slot, ideally. Slots are 12 seconds. These are just rounds of the protocol. And so that's why you have this like -12 all the way to 0. And the idea is, when we see a winning bid happen through the system, when are builders sending it? Are they sending it at the very beginning of the slot for the auction, or is it like near the end? And you can see it basically all concentrates right at the end. And that's basically because what happens, and this is now this next graph, what's happening is like a builder will send a bid early in the slot, and it has some value. What's happening is transactions are still coming through, like even to the public mempool. And so what happens is the builder can take those, and basically, again, because of the way MevBoost works, it just looks at this one metric, the value of the block, and me including my like ETH send to you that otherwise has no MEV, but has this like extra tip that's going to bump up the block value. And so because these are going to keep streaming in through the slot, basically, I'll keep bidding, and we'll end up with like this increase in the distribution where, I just keep spamming more and more valuable blocks until eventually one of them's taken. Again, this is problematic because it leads to this like latency war where builders now need to like both accumulate every transaction they can find and then also like spam relays with these blocks. So to get, well, at least to improve the situation, there is a proposal from Mike Nutter, also Justin Drake has been involved. Their work on the ultrasound relay. They want to roll out this idea of an optimistic relay, where basically, so relays today kind of do two things. They validate builders' blocks to make sure they're valid in the first place. They also do this like data custody thing. So they essentially want to say for like trusted builders, well, they're actually not even really trusted. The idea is that basically for builders who can collateralize their blocks, they're going to not do validation, and that's going to again shave off like some 200 milliseconds, let's say, of latency, which hopefully improves this builder game somehow. The idea is, I think, pretty fresh, and they have a proposal. We in the MevBoost community have been like discussing it some. If you want to check it out, there's a PR here. There's no link, but find me after or something. I can show you to you. Yeah, so it's an interesting idea. My thing with the optimistic relay is that it seems a bit, well, there's a couple issues, I think. But one of them is just it seems to like open up this like space for more insidious bugs if we say, okay, relays are suddenly going to like not validate blocks. But there's a conversation to be had. And then we'll just zoom in very immediately. So yeah, there's a hard fork coming up in Ethereum. Chapella, because there's now 2 layers, 2 forks. Capella and Shanghai, we merged them to form Chapella. That's happening very soon, and so there's been a lot of work around MevBoost, the relays, and also the builders to get ready for that. There's another big upgrade with 4844 and like our proto-dank sharding and the whole sharding vision. that'll be coming soon. Similar thing there. And then separately, we can think about, are there ways we can like implement additive protocol, censorship resistance techniques, to get around this like OFAC issue. Yeah, and so again, that's more of an open R&D thing, but something may come out of the pipeline there. So yeah, that was a lot. Thanks for sticking around. If you want to contribute, there's a number of links here. This is like my Twitter handle. Like you can DM me. That's probably the best way. I will call out. We just had a community call to start some like loose coordination around this stuff. There's going to be another one, I think, a week from today. Either way, we're coordinating on the Flashbots forum for this. So go take a peek there, and there'll be something about MevBoost community call number 1. And yeah, thanks for your time.
Questions for Alex? Questions, anyone? Go there. Go here, and then you. Is it okay?
Hey, Alex. Thanks so much for the presentation and explaining the concepts really well. Can you explain again how MEV can destabilize consensus? And also the second question is, how did you guys get MEV boost adoption to be so high?
I'll answer the second question because I think that one's a little simpler, which is, yeah, I'm not sure. So basically, Flashbots did a lot of campaigning, I think, towards the merge to like let people know the solution was there. Like people are already using its sort of predecessor with MEVGeth, and so I think for them it was like pretty straightforward just to like swap in the new software. But yeah, like honestly, I think this is an example where like incentives speak for themselves. Like I am kind of shocked that like it has the adoption it has, but also like for like the rational staker, all they see are like bigger returns from this MEV thing. So like, great. Yeah. So yeah, I mean, it's pretty wild, but yeah, I mean, yeah, definitely like Flashbots has like been pushing this as like a way to democratize MEV access, which is good for many reasons. So like, that's good that they're doing that. And then separately, yeah, I think people just like hear about this and the incentives speak for themselves. The other question was about how does MEV destabilize consensus? And yeah, maybe I didn't explain very well the first time around. So the idea is that, well, yeah, so the way I would kind of think about it is like MEV happens from transactions, but you could almost kind of zoom out and think about it per block. And so, some block is proposed for the chain, and let's say it has some amount of MEV. The problem comes in when this MEV is like, well, it kind of happened. It exists at all points in time, but it's especially a problem when the MEV is very high relative to, say, like the block reward or like the rewards of that block. And the reason why is because the next proposer can go and they can take the MEV, like however the MEV was like extracted from that block, they could basically just take it for themselves. Like you have a block in the chain, it's like a public data that anyone can like use. And so the next proposer could turn around and just like basically try to reorg you out of the chain and like include those same transactions for themselves. Because of this, you end up with this like almost race to the bottom where like if the incentive is high enough, like everyone just keeps doing this. And this happens like, there's actually a paper, I think probably the first place this was in like the academic literature was on the instability of Bitcoin mining or something like this. And it's the same problem where like if you had, I think in that context, like the problem gets a bit worse because the Bitcoin block reward could become so low in the future. And when that happens, then you could have like transaction fees that are orders of magnitude more than the block reward, where it's essentially the same thing. Yeah, does that help? Okay.
All right, we have our last question, then we're going to move on to Tarun.
I think the number of transactions on Arbitrum this month exceeded those of mainnet, and I'm just wondering, as Optimism and Arbitrum and other rollups proliferate, whether the dynamics with regard to MEV change at all, and are there any like different questions or considerations that we may need to think of in that modular structure?
Yeah, great question. So yeah, we're seeing these like L2s come online, and yeah, it's like kind of all the same questions we've been thinking about with L1 are like now we can ask, do they apply to L2? And definitely the MEV they do. Like a big difference is actually the fact that many of these systems today have like these centralized sequencers. Yeah, I mean, I could say a lot about this, but one interesting bit that just happened, basically Arbitrum was going to propose, so Arbitrum was seeing there was like undue load, like heavy load on their sequencer, like network, their software, the server, because basically searchers were like hammering it, trying to get like the next block. Because again, there's essentially this latency race where if I get the next Arbitrum block, I have this like advantage over every other searcher to like, extract the next MEV from the next block. And what would happen is they would basically had a mechanic where searchers needed to like, it would work out that the more connections you had to the server, then the greater chances you would have of having the next block. And what this meant is this high load on the Arbitrum system, and they didn't like this, so they're trying to figure out what to do about it. They actually proposed basically introducing some like proof of work back into like the network layer, such that you would essentially like have a proof of work required to like get a special slot, and then you would have one of these like privileged network positions. Of course, many in the community were like, well, why are we doing this? Like, you're basically just taking the MEV from the Arbitrum system and like putting it, into like ASIC or GPU providers, like manufacturers' pockets. Whereas instead you could take the MEV and internalize it to Arbitrum. You could like use it for like some public goods function, like all sorts of things, right? So yeah. Anyway, I'm kind of going on, but that was a fun example. Optimism too. I mean, it applies to all these systems. I think a lot of the L2 teams are thinking about, how do they handle MEV? It's definitely there, and yeah. Was that helpful? Okay. Yeah. Definitely a rabbit hole. Okay, I think that's it for me. Thank you all. I don't see there. Okay.
You're good.
Yeah.
All right, ladies and gentlemen. Well, thank you for sticking around with us all day long. We've had incredible presentations, incredible thoughts, and incredible research. And we thank you all for being a part of it. Just as a reminder, we have CryptoEcon Day here in Denver, but our next one is going to be CryptoEcon Day in Austin for consensus. So please, we'd love for you to all sign up. Everyone that did register for this event, you will get an email to register for that event as well. We'd love to see you in Austin. But here comes our final presentation of the day. We have Tarun Chitra, who is the CEO and founder of Gauntlet, who's going to blow our minds on NFT auction design. Here you go.
Cool, thanks. And it's probably been a long day for everyone, so hopefully this one won't be too technical. I did elide some of the math, so. But yeah, so we're going to talk a little bit about gradual Dutch auctions. So they were this thing kind of introduced by crypto people randomly, and if there's anything I've learned throughout all the papers I've written in this space, oftentimes crypto people have the right intuition, horribly wrong math, and when you try to write out the equations, you're like, okay, there's really something else here, some other phenomena. And I think in the gradual Dutch auctions, that is a very true, similar thing. And this is joint work with Kshitij Kulkarni, who's at Berkeley. Also thanks to him for helping me with some of the figures, and Mateus at Harvard. So, what is really the goal of an NFT auction? Well, if I'm an artist, if I'm a game, if I'm someone who likes to wait in line in front of Supreme stores, my goal is to really sell a batch of these things without necessarily knowing without knowing exactly how the price will clear. But I want to kind of construct a mechanism where I can easily unload supply and try to maximize my revenue or try to achieve some other type of social welfare goal. So you might say, okay, well, what are the different things you might want out of an NFT auction? Well, the first thing is incentive compatibility for the buyer. That means that the buyer who is bidding bids what they really think the asset's worth. The second desiderata is incentive compatibility for the seller. The seller doesn't have any reason to kind of cheat. Maybe, if it's a really rare NFT, they keep all the really rare ones, dump all the floor ones, and, sort of manipulate the price. So, you don't want the seller's incentives to be to do things like that. The third is price discovery. Can you match supply and demand? The fourth, which, I think is only really been accepted as a valid criteria since maybe the 2000s, is the auction is actually computationally tractable. The fifth is no side off-chain agreements. And the sixth is adversaries shouldn't be able to manipulate the auction modulo, solving discrete log, breaking class group stuff, whatever assumptions you make. And I tried to ask ChatGPT to make a joke, and it made a shitty one. So you might say, hey, can we actually get really ideal single item NFT auctions? And the answer from Miliones et al. 2022 is not really. You can't get this off-chain agreement piece and bidder incentive compatibility to match. They also show some sort of weaker seller incentive compatibility result, but it's not as strong. Okay, so shit, are we out of luck? Well, obviously I'm giving a talk, so hopefully not. So sequential auctions. So one thing is, let's say I'm an NFT creator. I have 500 items in my collection, and I want to sell the 500 items. Well, there's many ways to do that. It's a combinatorial auction. I could sell all 500 all at once and say, hey, someone who wants to buy all 500, buy all 500. Not great for price discovery because you're assuming there exists a buyer who wants to buy the entire collection. You could also do the opposite, which is sell them one by one, observe what happens based on each sale, and then adjust the price dynamically. And that's what a sequential auction is. It's sort of the exact opposite of the sell the whole batch version. And you can, of course, do anything in between, sell pairs, sell bundles, whatever. But the sequential auction is the easiest one to reason about. It also gives the seller a lot of control of adjusting the auction price to demand. And in some cases, you can actually get some good properties from sequential auctions. So in this picture, you can think of it as like at time one, the seller is like, all right, I'm going to sell this NFT for $1. They observe that, there's people who are not willing to pay, or they weren't able to sell it. So then at time 1.5, they sell a cheaper one to see if there's anyone who bites at 10 cents. And then, you might have a clearing price at 1.5 and 1.05. So the idea is that agents can show up at any time who are buyers, and the seller just sort of streams things and adjusts some notion of reserve price or posted price. Okay. So what are sort of the pros and cons of a sequential auction? Well, it turns a single n-item auction to n single-item auctions, like I was saying. It allows buyers to adjust their purchasing decisions to true demand. So for things where there's a common value, where there's not sort of like an empirical price, but there's more whatever the price is, whatever everyone agrees on of all the buying community, then buyers can adjust how they buy things in the sense that, hey, maybe a buyer notices a bunch of auctions have been clearing at a high price, and so then they decide, based conditional on that information, that they start participating in buying a bunch of auctions because they think there are people in the future they can sell to. Sequential auctions have this nice property. We don't have to really go into technical details of it, but sub-game perfect equilibria, this is sort of like a property you oftentimes find in things that are, say, solving poker or chess. And finally, computationally easy to implement in the sense of you post a price, someone takes it or leave it, that's it. The cons. Well, actually maximizing social welfare, so maximizing the utility of the buyers and the sellers, is extremely, extremely dependent on the precise utility functions of the buyers. That's not true for some other auction formats. So as just a simple example, if you have identical items, the difference between sort of the worst case equilibria and the best case is constant. But if you have bidders who have additive value, where their utility function is sort of super additive, you can never approximate an equilibrium. Another thing is, from a complexity standpoint, it's slow in the sense that if I have n items, I have to do n auctions, and that might not be ideal for you as the seller. And there's actually another kind of very simple economic fact about these things, which is revenue maximization for the seller depends on whether if the goods are complements or substitutes. If the goods are substitutes, it turns out you can approximate revenue. If they're complements, you can't. And that's sort of a weird property of sequential auctions. Okay, so before we talk about what a GDA is, and a GDA is effectively a crypto person's interpretation of sequential auction literature without reading the sequential auction literature, is that sequential auctions have this problem of interdependent valuations. And what an interdependent valuation is my value for the item depends on what other people's value for the items are. And so if other people send signals, e.g. they buy certain auctions at a really high price, it changes my value for the item. So, this is the Supreme, the reason I bring up the Supreme store is Supreme and NFTs both have this property of like, the more people you see waiting in line, the more you think the thing is going to resell on eBay, right? And that's generically also true with NFTs. That means I'm interdependent. I'm dependent on the valuations of everyone else. And interdependent values are actually very hard to analyze. So in this example, we have two bidders, these two robots. One bidder has a value of 10 cents, and one bidder has a value of $1. And at time one, the seller says, okay, I'm going to sell the item for $1. But the first person says, if the other bidder buys this, I'm going to increase my value because I know that there's someone whose value is at least $1. And because of that, I think there might be more people whose values are over $1. And similarly, the second person says, if someone buys it, I will raise my value because that means there's some demand. So the idea is I'm adjusting my valuation based on observed demand. So let's say the second bidder buys that, and now the first bidder, as you can see, increases their value, right? Their value changed because of other people's beliefs. This is not independent valuation. And if you've ever taken sort of any econ auction theory class, 99.9% of auction theory assumes independent valuations amongst these bidders. This is the opposite of that, right? I changed my value because someone else's value went up. And okay, how many of you in this room have ever bought an NFT? How many of you have bought an NFT because you heard of it because like someone posted about it? Right. This type of behavior is endemic to NFTs. So when you're thinking about designing the auctions, you have to have this built-in thought of, well, I really have to think about what other people's values are, not just my own. Okay, so now what happens is bidder one increases their value, and then the next auction, the remaining item is too expensive. It's $1.50. And the second person also says that their value didn't change. And at time step 2, the seller says, okay, I guess there's no one who wants to buy $1.50. Let me try making it $1.05. And look, now you get an equilibria where both parties end up with an item. And in the independent values world, if we went to the beginning with this guy, the independent values would have said, bidder one never wins an item in this auction, right? And so you get very different clearing equilibria, very different quantity clearing in these interdependent auctions. So this is just to set the stage as an example of why NFT auctions have different properties than, say, even MEV auctions. There's some interdependence there, but here it's really intrinsic to the buyer's behavior. And of course, our friend is unhappy because he started with a lower value. Okay, so gradual Dutch auctions, sequential auction mechanism designed by Dan Robinson, Frankie, Andy, and Dave. One of the interesting things about it is, unlike other auctions, it's a Dutch auction style auction. So in the previous examples, we had a pure posted price mechanism. The seller is posting a single price, and that's the price. The gradual Dutch auction does something different. The seller posts a price, and then it decays over time. So the longer the item hasn't been sold, its price automatically goes down in some schedule. And so that's the actual key innovation that if you look through the auction theory literature, no one has ever studied that type of auction. They study these posted prices where the auctioneer says, I'm willing to sell at $1, and it's always $1 for all time in the future, as opposed to it's $1, it's been an hour, now it's only 90 cents, it's been 2 hours, it's only 80 cents, ... These mechanisms are called dynamic posted price mechanisms in the auction theory literature and sort of algorithmic game theory literature. And the interesting thing is these Dutch auctions, as many of you might have seen, are actually pretty good in a blockchain scenario. And so I'll give you some heuristics for why that is, but actually formally none of the statements I'm saying are actually true. There exist some edge cases where this is not true. But Dutch auctions have this thing where the communication complexity for Dutch auctions is actually, on average, very low. The worst case is potentially exponential in the number of bidders, but the average case is actually very low degree polynomial. Whereas ascending price auctions, so that's like the guy at the raising his hand saying like, anyone want to buy for 1, anyone want to buy for 105, anyone want to buy for 103, 108, sorry, I can't do an ascending number in my head apparently. There's a lot of communication complexity between the auctioneer and the bidders because people are kind of interacting to say what the price they're willing to take is. So Dutch auctions are actually, they're sort of, even in normal finance, they're extremely common. Auction theorists hate Dutch auctions because they are what are known as indirect revelation mechanisms, in that they have a lot of path dependency when you try to analyze them on the sequence of bids and the order in which they were received. And so then that gives you all these impossibility theorems, so people hate Dutch auctions. But there's a David Parkes paper, 2008, that shows this communication complexity result. Okay. So the first question you might say is, we wanted all these incentive compatibility results. Do they exist? And surprisingly, and that's what this paper we wrote is, shows that even for interdependent values, there are scenarios in which this auction can be made incentive compatible, which means that even though people have this heuristic intuition for why this Dutch auction should work for these valuations where people's values depend on each other, you actually can prove formally in a lot of cases that they do have that property, which is quite surprising. And the second thing is, what kind of revenue guarantees you have, and we sort of show some under more strong conditions of sort of bounded price anarchy type of result. Okay, so what does a gradual Dutch auction look like? I'm going to give you my 3-year-old crayon version. The x-axis here is time. The y-axis is the logarithm of price. So I did it in logarithmic terms because the paradigm paper uses things in log price space. And these charts are easier, and I'm really bad at drawing things. So I can only have to draw lines. So the idea here is, auction 1 starts at a price that's a log price, that's the top of the solid green line. And as time progresses, if no one buys at auction, the price decays along that dashed line. Same with auction 2, which is the yellow, same with auction 3. But notice the heights of the initial prices are going up. They're ascending. So auction 1 might start at $1, but then if no one buys it, it decays to 5 cents. Auction 2 will start at $2, but if no one buys it, it'll decay to $1, then it'll decay to 5 cents, ... And this sort of ascending, descending behavior is actually where a lot of the nice properties of this auction format for interdependent values show up, which is, again, very surprising. If you read the original blog post, there was none of that. It was not obvious that this particular sawtooth thing actually has some nice properties. But we'll talk a little bit more about the exact incentive compatibility statement in a second. Okay, so technically the paradigm version of this is actually not itself incentive compatible in all scenarios. But what we show is you can modify it, and look, the only difference between this one and this one is the heights are the same, but the curves, the decay rate, is not flat anymore. It has this curvature, and this curvature depends on the utilities of the user. So we show that if you modify this decay rate, you can get these incentive compatibility properties. So right idea, slightly wrong for incentive compatibility. This is the original one, but it's very simple to implement. Slightly hard to implement, but you can get these nice properties, and that's sort of the main result in this paper. Okay, so we're going to do the bare minimum of the math. You'll see later that I rug you and do not give you the actual final conditions, so sorry. But a gradual Dutch auction, single item, dynamic posted price, that's all your jargon. A1 through AN. There's auction AI, starts at time tau I, and there's an ascending sequence of times. So again, tau 1 is when the green line is active, tau 2 is when the yellow, tau 3 when the orange. The price of the auction is 0 below tau I. So as you can see here, auction 2 is inactive until the time where the yellow line is above the y-axis. And after tau I, it's strictly decreasing. So the highest price that auction will ever have is the initial price, and then it's decreasing. And then the other thing is the sequence of initial prices, so that's the height of the solid lines, is strictly increasing. So you have this thing increasing, decreasing, increasing, decreasing, and like I said, you get this kind of sawtoothy wave-looking thing. But the waves are increasing, if that makes sense, as you can see here. And so the interesting thing about this, and this is sort of, maybe if you've studied like online marketplaces, somewhat obvious. Everyone who's ever used an Uber, you're the victim of the right picture in this, which is dynamic pricing can be much better for revenue optimization. And sort of the intuition is that you can kind of capture people a little closer to where they want to be. All right, so more formally, the precise prices that the paradigm auction posts are of this form. So they have exponentially increasing heights. And so remember, when we're in log space, so again, this is why we did this in log space. So I could like linearly say, you know, the green is at log A, the yellow is at 2 log A, the orange is at 3 log A. And then exponentially decaying with a fixed slope. So you can think of this lambda as the slope of that line, of the dashed lines, and they're all the same. And then this indicator function is just this idea that like, you know, the auction is only active after a certain time. Before that, it's 0. So the interesting thing is there's sort of a wash trading spoofing attack against this auction. And what it corresponds to is the auctioneer buys some of the first auctions. So they buy the first, say, 10 auctions of their auction. So that pushes the price up to what the 11th auction price would be. And if they know anything about the demand curve, they effectively can force people to miss the early, cheaper auctions and be forced to buy the later, more expensive auctions. And so I call it wash trading because in some sense, the seller is buying their own supply, and eventually will maybe get rid of it. But they're doing it in a way that it's not obvious to the buyer. The buyer doesn't know that they're getting front run in some sense. And you know, if you go write this out in terms of the supply and demand curves, you can show some conditions under which basically the seller can force the buyers to pay a higher price than would be sort of a neutral market clearing price. This picture tries to show it of like this P star is sort of like the optimal price. You have P star on the y-axis, Q star on the x-axis, price and quantity, of course. And the idea is that you kind of have this deadweight loss where you push the quantity down but the price up when you do this front-running thing. Okay. So this means the original GDA is not incentive compatible. In the paper, we give conditions for when the spoofing works and doesn't work. It's pretty straightforward math, nothing like that hard. So do GDAs not work at all, or what's the story? Well, again, we have a talk for a reason. So I'm not going to actually talk about any of the math because it involves a combinatorial object called a matroid, and probably not the ideal time to define it. But I'll give you some intuition in this slide, and then we can go to questions. So there's a phenomenon in interdependent auctions that's been known since the 1960s called the winner's curse. And the winner's curse was first observed in the late 60s, and I believe Vickery wrote the first paper analyzing it, which is the US government was auctioning land rights in Alaska to oil companies. And so each oil company was allowed to go to this piece of land and stick one probe in or send one sonar in, whatever. I don't know what the measuring device was, but they're allowed to take one sample, measure how much oil they found, and then that was the only data they were allowed to use to construct their bid for the auction. Because if someone was like, hey, look, I have this land that has a ton of oil in it, like, how much are you going to bid? No one's going to bid on that, right? So the government has to give you some ability to get some information about it. But if you think about it, in that piece of land, there's just a fixed amount of oil, right? And assume everyone can extract exactly that amount of oil, then there's sort of a notion of like, everyone should have the same true value if they knew the exact amount of oil in that plot. But instead, I'm taking a sample. So I take a sample, you take a sample, you take a sample, you take a sample. The irony is if our samples are independent, then the average of all of our samples, our estimates for how much oil, is actually the true amount. But the amount that I measured might be very far from that. Like I could have measured the place where it was the maximum amount of oil, so now I think this land is filled with a ton of oil, so I bid way higher than everyone else. And that's the winner's curse, is that the bidders kind of have a common value. There's a fixed pot of oil, there's a fixed dollar amount, whatever, currency amount for it. But the person who wins the auction actually loses because they're the ones who got the spurious highest sample. And so this actually happened, and people analyzed this in the 70s, where basically everyone who won these oil auctions ended up being unprofitable and going bankrupt. And there's a huge trail of tears of this. So anyway, this winner's curse thing also come to NFTs. I probably don't need to tell you that given all of the memes of Wojaks. But the interesting thing is dealing with these winner's curse things, it turns out kind of somewhat in an indirect way, these matroids, which are sort of combinatorial objects that encode the most generic thing you can do greedy algorithms or gradient descent on, represent the things that avoid those. You know, that's sort of, the intuition is that these combinatorial structures are meant to like kind of avoid these kind of cases. So, as I said, I'm going to rug you, but I asked ChatGPT why, and that's your answer. Cool, that's it.
Questions for Tarun? Made the first one here.
Hi. So this is super interesting. I was wondering regarding the last issue that you mentioned, the winner's curse, where it's like unfavorable to the bidders because they couldn't basically come together to figure out the fair amount. Do you see potentially like zero knowledge, like multi-party computation, like disrupting this space?
Yeah, that's a great question. There is definitely a world in which, you know, the model of this type of stuff, and so this goes back to Milgram Weber in 1986, is, and pretty much everyone still uses the same model, even though it has some deficiencies, especially for blockchains, because there's some public revelation of information, is the idea that everyone who's a bidder has a private signal. And the private signal in the oil case is like, I stuck in the probe and I found 5 gallons of oil. And someone else stuck in a probe and they found 10 gallons, right? That's our private signal. And based on the signal, we have a utility function that tells us what our bid is. Now, the question is, can we aggregate our signals in a way that we don't reveal our signals, evaluate the utility function at that point, and then, and you can 100% do that with MPC and ZK. There's no way, there's no doubt that that would work. I think the question is, like, when do you have adversarial entities who want to cooperate just enough to aggregate that? And I actually think that happens a lot more in like normal finance, because like banks sort of, you know, you could argue LIBOR, which is sort of the London interbank offering rate, is effectively doing something like that, except, you know, there's a trusted aggregator. And you could imagine actually being in a world where people tell you their private rates, but you only learn the aggregate rate. And I think in general, these NFT auctions actually could benefit a lot from that. So yeah, for sure.
Hey, thanks for the talk, Tarun. I wanted to ask, I don't have a very good intuition, but I've seen some of the auctions or some of the curves. Did you have like a basic Dutch auction that is declining with time, or and then if there is some demand shown, let's say you are selling some set of NFTs, the price would go up based on some kind of a curve or based on some conditions. Is this incentive compatible? I would guess not, and why? I mean, this intuitively sounds good to me, but yeah.
Yeah, that one actually it has a very similar spoofing attack, which is the seller starts to just fake demand at certain points so that people, like it goes back up and then people buy because they see that fake. This is where this interdependent thing matters, right? In that example, the first bidder was like, I only value this thing at 10 cents. And then the moment they saw someone else say it's $1, they're like, it's at least $1, right? So these interdependent valuations are weird because if the seller has any ability to like push the demand curve up with a small amount of quantity bought, then they can sort of trick demand into people into adjusting their values to think that's the true value. The key is actually like choosing these increases and decays such that the seller is forced to hold a lot of inventory. Because the more inventory you force them, it's almost like slashing them. Because they have to like just hold a lot of inventory that might go to zero. And so that's where you could make the same thing incentive compatible. I think the nice thing about these GDAs is they're really easy to implement and audit on chain comparatively. And I think like the security properties proven in the GDA audit are amazing. Now, we all know Art Gobblers was a kind of shitty NFT, but you know, I think I hope people don't like forget the mechanism that actually is very cool, in spite of the fact that it may have been used on a kind of not so great project.
Thanks.
I think you mentioned like how complements is harder than substitute and combinatorial auctions. Why is that?
Yeah, so that's a good question. So there's a property of a function on sets. So say I have a base set S of items. I have the power set to the S of the power set of items. And I now consider a utility function from 2 to the S to, say, the positive reals. A function substitutes have this property that you have decaying marginal utility. That means if I take a bundle and I add another item, the difference in utility between the added item bundle and the original bundle is sort of decaying. It's sort of saying like the slope is sort of decaying over time. Those kind of concave functions are called submodular functions when lifted to set functions. And those have these properties that are kind of known that you can find their optima very easily, or you can at least approximate their optima. There's a lot of like basis pursuit style gradient descent algorithms that do that. But complements, however, have this thing where like you could have the utility increase or decrease and it becomes a sort of generic non-convex optimization. So the complexity results come from that, more or less.
Okay, thank you.
Any additional questions?
So if you were to launch your own NFT collection, how would you structure your auction?
That's a good question. I actually like the design of these like momentum dynamic things, but I don't think there's just like an easy way to write them such that either the smart contract is not vulnerable to like lots of weird wash trading stuff, or MEV is like really high. These gradual Dutch auctions are actually quite good against MEV, and like this is actually something I'm still trying to wrap my head around. But like in practice, if you look at the performance of the Art Gobbler auctions, there's actually much less MEV around them than there are around certain mints where people just try to buy up, you know, the whole block and resell them. And part of that has to do with the fact that like these price schedules mean that like, okay, yeah, I miss it at time T, I miss someone else buys it. If the next price is really high, like, you know, let's say the initial price is $2 and it goes down to say 150 and then someone buys at 150 and then the next auction starts at $4. Well, if no one has a value above 150, then I can get it again at 150. And so this relaxation property is actually super nice about these and makes the MEV part less attractive. But I don't have, it's sort of a very complicated way of understanding why that is. I tried formalizing it and I gave up at some point. But I think like these are actually pretty good for MEV, which is why I probably would use these. Yeah.
Tying back to what we were talking about, or what you were talking about, that wash trading is kind of the Achilles heel in a lot of this, that basically the seller can pretend that there is more demand than there actually is. What about like a naive approach that you actually keep some portion of the sold funds, like the marketplace or some third party, keeps this? I mean, or it's just in the mechanism, and then basically this pod gets redistributed back to like the participants, but basically just have like a naive way like this to prevent or minimize the wash trading. Is it doable, or is it?
Yeah, I think like those things can work. The hard part is like, how do you choose the distribution function? Because like if the distribution function is gameable in some way, then like you run into kind of the same problem. You know, the airdrop distribution problem is actually just like very hard, and I think the blur type of tactics of like these like seasonal like repeated airdrops that you don't know the precise conditions of. Somehow I think the ZK MPC stuff will actually allow you to do much better versions of these redistributions, because you actually can hide a lot more while committing on chain to like, this is the strategy and we're not changing it. So I think like the future evolution of those airdrop, that type of scenario, I'm using the airdrop example because Blur is obviously top of mind for that, but is that like you could actually make this kind of like airdrop where you commit to a strategy, you commit to a redistribution strategy, so I can't change it, but then it executes later. And again, yeah, that requires more cryptography.
Any additional questions? Tarun, any parting thoughts on this? Anything crypto economics? Anything generally?
You know, I think as much as I personally have a distaste for NFTs personally, I find the space of like mechanisms people have made kind of wild, and I think there's a lot of open problems there. Like kind of like what you're talking about, redistribution stuff is like equally something worth thinking about. And I think MEV and NFT stuff are like very related, and like I think people think they're like completely worlds apart, but there's a huge connection.
Is there a way you can dive deeper on that? I don't know how they're overly related specifically.
I think the main thing is like they both have these like auction-like structures, and they both have this notion of, to some extent, interdependence. Now, MEV has a bound on how much interdependence there is because, you know, let's say there's a sandwich attack and the maximum possible profit from the sandwich attack is $10. Well, if I see someone else submit a bundle, let's say, suppose I'm a relayer and I receive the bundle, I might just copy them and like give a slightly higher gas price, but I'm not going to do that arbitrarily high. I'm only going to do that until the $10 max profit. So this bounded profit aspect of MEV is different than the NFT case where you can just go up arbitrarily, but they are quite related when you're in the regime where you're not near the max profit limit. So, if that makes sense.
It definitely does to me. Anyone else? Anything else? Tarun, thank you very much. Oh, wait, one more question.
I had a question about the other paper, the commit reveal one.
I'm going to talk on that on Saturday. So.
Okay, then I'll ask then. Okay. Oh, can I ask now?
Sure, yeah.
Okay. So can you do them together then? Like have commit reveal in these like.
Yeah, that's a good question. I don't know how to do Dutch auction commit reveal. I think you actually do need like ZK where you like prove that the price increment function decayed at the right rate. I don't think you can just do like Peterson commitment style things. You do actually need to like prove that the price decay was not manipulated. So, but yeah, I think you're right. I just don't think it's as simple as the thing we have in the commit paper.
I see. Thank you.
Thank you for your time.
Thanks.
That's it. All right, everyone, thank you very much for a great informational day. We hope you follow us on Twitter, follow us on all the socials, check out our website at cryptoeconlab.io, and we'll see you at ETH Denver. We'll see you at the conference, and please, if you want to talk to any of the speakers, team members, we have about 10 more minutes left. Feel free to do so, but then we will head out of Coors Field.